Okay, hi everyone. Welcome to CS50 quiz preparation. Goal of today is going to be to help you all feel prepared to tackle the quiz. And so before we started, just thought we'd go over a few quiz logistics, just to make sure that everyone's on the same page as to what the expectations are, what to expect from the quiz, what it's going to be like. So let's go through a couple of the logistics. In terms of when you'll be able to work on the quiz, we're going to release the quiz tomorrow, Saturday the 10th at noon, and you'll have up until Thursday the 15th at noon in order to turn it in. You'll turn it in via Submit 50, the same way that you've turned in all of your other assignments in the course so far. And even though you have this wide window of time, the expectation is it's not going to take you that entire amount of time to work on the quiz. We're giving you a wide window such that you have some flexibility within your own schedule to decide how and when you work on it. If you want to get it all done over the weekend, for instance, you're welcome to do that. If you're busy over the weekend and want to spend time on it during the week, that's fine too. If you want to start it on Saturday but maybe come back to it a little bit later after you've taken a break, totally fine as well. So it's up to you how you choose to budget your time. It's not going to take you that whole time from Saturday to Thursday, though. The quiz is open book for any and all non-human resources. So you can turn to any of the course resources, whether they be the lectures or notes you've taken, section materials, anything you find online. You can also look to things outside of the course. You're welcome and encouraged to be Googling things, looking things up, looking for other questions that have been posted on the internet elsewhere. And the only thing that you can't do is turn to a human resource. So you won't be able to ask a friend or ask one of the TS for help with the quiz. It is designed to be individually based. So it's entirely your own work. The only exception to this rule, the humans you can turn to, are the course's heads for clarification questions. So not for like, can I get help on this particular question? But if part of the question is confusing to you or you're unsure about the expectations, you can reach out to heads@cs50.harvard.edu and we can offer some clarification. But aside from that, no human resources for the course of the quiz. Again, you'll submit the quiz via Submit 50 as usual. And so that's the general logistics for the quiz. Questions about quiz logistics? Yeah?
Not logistics. What is the structure of it going to take? Is it going to be like questions like complete an exercise, or is it going to be just like what's the general structure of it?
Oh, good question. So questions about what the structure of the quiz is generally. Generally, it'll be a number of questions, each of which is likely going to have multiple parts. And the questions are designed to be more based around the themes of the class. So there'll be a little bit less problem set-like, though certainly there will likely be some code implementation where you're asked to write some code, whether in C or Python, for instance. But there will also be a lot of questions that are more short answer or write a paragraph questions that are designed to get you thinking about the ideas and the themes of the course, thinking about the ideas, and writing a response to those as well. So it'll be a mix and match of both. And it'll be similar in spirit to the types of questions that have been asked on the test and quizzes in years past, and Athena will talk a little bit more about that as well. Yeah? Good question. So is it timed? You'll have the window from Saturday at noon until Thursday at noon to work on it, but within that window, we're not time constraining it any more than that. So you're welcome to start on it, work on it a little later, a few days later if you want. How you distribute your time within that window is entirely up to you. It's not going to take you that entire amount of time, but we're giving you that amount of time to let you budget your time around your other constraints, however works best for you. OK.
Oh, there's another question.
Oh, question? I think the quiz preparation guidelines suggest like each question is probably going to be about half an hour. You can budget a little more for some questions, a little bit less. And you can take a look at like the past quizzes for a general sense of their approximate length.
OK, great. So in terms of how to prepare for the quiz, already you're great. You guys are here. You guys are watching this, this quiz review. But we have some other materials in the course generally. If you go back to lecture notes, which are great, the source code, slides, and videos, really great resources out there. Every lecture comes with a set of notes. So we have staff members going through and writing out these notes for you guys to use. You can also refer to these during the quiz. It can be really helpful. If there's some part of the quiz or some part of like a topic that is a little bit confusing to you, but maybe not worth watching a whole lecture to go through, we also really recommend checking out Doug's slides or Doug's shorts, which are linked on the course website for that particular week. Well, you guys are already here, so there you go. And then one really great resource that we do make available to you guys are past years' quizzes and tests. These are going to be really good to give you guys an idea of the questions that we ask, the sort of answers that we expect. We also make solutions available to you. So one thing you might try to do is look at a question, see how you might try to solve it, and then look at the solution that we would have expected of students, just to give you an idea of what we're going to be asking you to do and the sort of format that we're looking for. And then, of course, if you go through the problem specs, that will be a good place for you to see what are the sort of questions that we've asked you in the past, what sort of background have we given you for problems to help contextualize. A lot of that contextualization will be really helpful, or at the very least will give you an idea of how you can contextualize some of the problems that we're going to ask you on the quiz. So questions about this in general, how to prepare, what resources are available to you. Okay?
Okay. One other resource to take advantage of is there will also be office hours between the end of this quiz preparation session and the start of the quiz. You can check the course website for details on time and place for that, but also another way to get additional help, ask some quiz preparation questions as you go through the sample questions or are thinking about the topics that we talk about here today or in your own preparation. So definitely feel free to take advantage of those office hours as well. They're designed for help with preparation for the quiz. What questions do you have before we move forward with actual course content? OK, with that, what I thought we'd do is before we actually get into a week-by-week look at the semester and the topics that we've talked about, is to sort of think about things in the big picture, which will be helpful for contextualizing and framing things when it comes to the quiz, in particular considering the themes that we've talked about over the course of the semester. The big ideas that you should be keeping in mind as we go through the entire semester as the things that keep coming up and again, the reason why we're doing some of these things, why some of the course material is important, and trying to frame the semester in terms of these themes and thinking about how the themes weave their way through the course will help you to get a broader understanding of where we've been, what's going on within the class, why things progress in the way that they do. And so I thought we'd spend some time talking about those themes, what it is that they mean, and why it is that they're important, and then we'll talk about them as we go through the semester as well. But starting with the first one, which is representing data. And so this has been a big one throughout the course of the semester, whereby even from the very beginning, where we started talking about like binary and how we can use binary to represent things like numbers and letters and images and videos and so forth, which we'll talk a little more about later. Like that was a way of representing data. But then as we progressed our way through the course, we were looking at more and more sophisticated ways of representing data in different formats, right? If you have a bunch of data, how do you want to organize that data? Maybe in an array, maybe in a linked list or a hash table or a trie. We looked at a number of different data structures, each of which has their benefits and disadvantages, but all different ways of trying to represent data and information inside of our computers, which ultimately only understand sequences of zeros and ones, and figuring out how to pattern those sequences of zeros and ones in such a way that they're meaningfully representing data has been one of the big challenges of the course and one thing that we've seen again and again and again. And crucial to all of that has been the second theme, which we're going to talk about today, which is abstraction. So this idea of sort of moving up from lower level details and thinking about things in terms of them a little more conceptually. So we thought about, for instance, characters on the screen, so letters, as really just being abstractions over the sequences of binary digits that they represent. And we'll talk about that a little bit more. We talked about using functions as a general way of being abstractions that are abstracting away the behavior that a particular function is actually performing. We talked about data structures and how we can think of those in terms of abstractions if we organize data in a struct, for instance, that has a whole bunch of properties, another thing that we'll look at. And so abstractions weave their way through the course as well, and another thing to definitely be on the lookout for as we go from one part of the course to the next.
And then next we started looking at things like algorithms. So this was the idea that we had a problem and we wanted to be able to break this problem down into steps that our computers could then execute. And we talked about things like, you know, how do you make an algorithm computer executable? How do you take a human operation and make that into its simplest step so that you can then program a computer to do it? And in the process of this, we also talked a little bit about run times. How long does it take my algorithm to run? How efficient is my algorithm? And of course, throughout the course, we've talked a lot about design. How do I design my algorithms well? How do I design my programs well so that they are clean, efficient, and aren't doing anything unnecessary, for example? And then finally, big theme of the course is trade-offs. You see this a lot in how we represent our data. Some things tend to be better in terms of memory, but not so great in terms of time. and the reverse is usually true. If something is really great in terms of time, tends to be not so great in terms of memory. So these trade-offs are something that you definitely want to be looking for as you're studying for the quiz and looking at the materials from the course. So, did you want to?
Oh, one more theme.
Oh, we had one more theme? Oh, and of course, security. So security is a fun one, definitely a little more relevant in the latter half of the course when we talk about things like SQL injection attacks, but also still relevant in the earlier parts of the course where we talk about things that could go wrong. So for example, you all might remember garbage values in arrays, or potentially things like writing beyond bounds of your arrays. It's always a good idea to ask yourself, in my program, where could something go wrong? Where could an adversary try to make this operation fail, etc. Okay, that is the last theme. What questions do we have before we actually dive into the material here?
OK. These themes are just something to be on the lookout for as we go throughout week to week throughout this semester. So be thinking about how the topics we talk about integrate with the themes, and we'll be talking about that as well.
OK, so we're going to take a little throwback to Scratch, computational thinking. You guys might look at this and think, wow, we've already done so much. This is like child's play at this point. But we're going to go through it. If you have questions, don't at all hesitate to ask. This was a lot of the foundation of the course on which we built up to a lot of the work that you all have been doing now. But once our fundamentals are really good, we can always build on that a little more. So we remember. Well, actually, I don't want to do binary. You can do binary.
All right. So at the fundamental level, at the very beginning, when we were thinking about what a computer is, what it understands, it's really all just bits of data, where a bit or binary digit was just a digit that could be 0 or it could be 1. And everything else in the course, from the programs we've been writing to the data structures we've been creating to the web servers that we've been running in these most recent weeks, have all really fundamentally been based on this idea of, OK, there are bits that can be 0 or 1. And because of that on or off nature of the bit, we can begin to represent information. So the first thing that we did, for instance, is say that using these binary digits, we can represent numbers. And maybe with only a single bit, we can only represent 0 or 1. But if we take 8 of those bits and put them together, we end up getting what we would call a byte. And of course, 1,000 of those is a kilobyte. 1,000 of those is a megabyte. And we can come up with bigger and bigger ways of representing larger and larger amounts of data. But really, at the end, it's just zeros and ones that are being used in order to represent those numbers. And so one of the first things that we did was talk about, OK, how do we then take these binary digits and use them in order to actually represent a number? Like, what number would this actually represent? And the way we did that is assign, in the same way that we had like a ones place, tens place, hundreds place when we were dealing in a base 10 decimal system that you probably learned early on. In binary, we have the same thing, but with powers of 2. Where over in the rightmost position, we have 2 to the 0, or the ones place. Then next, we have 2 to the 1, which is the 2's place, the 4's place, the 8, the 16, 32, 64, and 128. And if you look at this number, it's really just going to be like 4 plus 8 plus 16. And you can do the math and figure out what number you get as a result of adding up just the places that have a 1 in them. And so using just 0 and 1, we ultimately had the expressive power to be able to represent any integer, for instance, using just patterns of zeros and ones in binary. And using those patterns, we were then able to create some abstractions in order to represent not just numbers, but higher level concepts that are really just fundamentally based on the same idea of zeros and ones in binary, for instance. So for example, one thing that we spent a lot of time on early in the class was representing characters. So if you want to represent a letter like capital A or capital B, how would you do that if all you have are numbers? Well, what we talked about was an encoding called ASCII, this idea of, all right, in order to represent each letter, let's just all collectively agree that each letter or each character, not just the letters, but exclamation points and periods, other punctuation and symbols as well, is ultimately going to be mapped to a number. And so capital A, for instance, was mapped to 65. Capital B was mapped to 66. All the lowercase letters were mapped to a different number as well. And so what were the takeaways of that? Well, number one was that it probably wasn't all that important that capital A is mapped to the number 65. Like, the number 65 isn't as important as the fact that we just collectively agreed on this standard some number of years ago, such that everyone decided capital A is going to be represented as the number 65. And as a result of that, since everyone's in agreement, when a program on a computer receives like the number 65 encoded in binary, it can look at that and understand it as the capital letter A. There are other things we can draw from here too, like understanding that because the capital letters and the lowercase letters differ in terms of what number represents them, if in a C program you were trying to compare, like, is the capital character A equal to the lowercase character A, that would come out to be false, right? Those two are not the same thing, even though they're both the letter A, but in terms of what's actually being represented in memory, what the C program is actually doing when it's running that comparison, it's checking, okay, is 65 equal to 97? Well, no, it's not. And so we're able to draw inferences about the way that our program is going to behave just by understanding this relationship, this mapping between characters and the numbers in ASCII that ultimately represent them. And we were able to use this in any number of ways. Later on in the course, we saw that in our resize recover, for instance, we were able to represent images by using RGB encoding. In other words, some amount of red, some amount of green, some amount of blue, in order to represent a color or a pixel on the screen, just one dot on the screen, whereby each red, green, blue value is 8 bits, or just 1 byte worth of information, so ranging anywhere from 0 to 255. And you can imagine that a color that has a little bit of red, but a lot of green, and a little bit less of blue, but still a fair amount of blue, might come out to be a color that looks something like this. And so just by using 3 bytes worth of information, 1 byte a number for red, another number of 1 byte for green, and another number for blue, we can represent millions upon millions of different colors that are ultimately just combinations of these bits. And it's this computer that can understand the context of what these numbers should be interpreted as, that can therefore determine what pixel should show up. So a program that deals with images might interpret these numbers to be a color, whereas a text program might interpret these as their relative ASCII values and try to interpret each of these as characters, for instance, and try to display them that way. Ultimately, it's all just zeros and ones. What's important is the context in which they're in and how a program chooses to use that context to do something useful or meaningful with that information. Athena?
Yeah. OK. All right. And then we're back to algorithms. So when we first sort of introduced algorithms, we talked about them like black boxes, right? You don't really know what the algorithm is doing, but you do know that if you give it some input, it will do something and give you some output. This input could be anything in terms of strings, integers, anything like this. But really what we were saying with this is that the behavior of this algorithm, the behavior of this program, is abstracted away, where at the end of the day, maybe you don't care how the algorithm does it. What you do care about is that output that you're going to get. So in terms of things like this, this was a huge abstraction, right? And when we start talking about functions, functions are really themselves algorithms in a way, right? Maybe not a helper function that is a little bit small, like something that converts a letter to uppercase or lowercase, but maybe a function that is actually handling, opening a file, where you might imagine that what you're really caring about is that input you're putting in and that output you're getting out. I'm not sure if there's more to this. So if we move back to Scratch, Scratch let us implement functions, let us implement algorithms in these sort of very simple blocks, where we might imagine that if we wanted to have our sprite move 10 steps, maybe we don't necessarily care how it is that it's moving 10 steps, but we do care that if we say, hey, move this number of steps, the output that we're going to get is that we literally see our sprite move that number of steps that we've specified. Beyond that, these algorithms are really depending on variables. They need some way to represent the state that they're in so that they can continue to function. Function. And the way we were doing this in Scratch was saying, hey, I need to make a variable. I need some way to represent this data so that my program, my algorithm, can actually function the way I need it to function. And what we were doing is saying things like, set this variable equal to some value. So in this case, we are setting it equal to 28 here so that in our greater program, we can now use this value 28. Then we started to get a little bit more sophisticated in our programs. We started to ask questions, right? Maybe the things that I want to do are going to be dependent on some state of a variable, right? Maybe if my variable isn't equal to 28, I want to be doing something different than if it is equal to 28. And so we introduced this idea of conditional statements or conditional branching, where we might ask, OK, what is the state of this variable? If it is the state I'm expecting, perform one action, otherwise perform another action. And in order to ask these questions, what we're really asking about is this idea of true or false, or these Boolean values, right? Where we might be asking, OK, is something equal to something? And the answer to that is either going to be a true or a false. But sometimes the questions we ask need to be a little more complicated. Maybe I care about the state of 2 variables, or I care about the state of 1 variable or another variable, or maybe both. So we have this idea of these logical connectives, where and we expect both sides to be true for the entire expression to evaluate to true, or where we might expect at least one of them to be true for the entire thing to evaluate to true, or if both of them are false, they're both going to be false. And of course, we have this idea of, well, if something can be true, we can always flip that sign and make it false. So we can just easily flip back and forth. And we remember these fairly simple Boolean expressions that actually are really the foundation of some of the more complicated programs that we ended up writing later. And finally, once you have this idea of an operation you want to do and some way to track the state of what you have done, or to be able to ask yourself questions and do things conditionally, the next logical thing you might want to do is say, OK, great, I've figured this out. Now I want to do it again, and again, and again, and again, and again. So loops were the next really big, powerful tool that we introduced to let you say, OK, you have this piece of logic, you have this idea, and you need to be able to repeat it. Right? Loops in Scratch were fairly straightforward. They literally just let you do the same thing again and again and again based on some variable where you said, OK, I need this to repeat 10 times, 14 times, 28 times, 42 times. Where the idea here was, if you take some bit of logic, you can simply repeat that logic and accomplish the goal that you're going for. So before we move on to C, those were sort of the fundamentals that we looked at in Scratch before we then said, OK, you have this idea, you have this graphical interface, but really what you were doing is building programs. You were putting together logic by putting together these puzzle pieces. So before we move on to C, questions about Scratch? OK.
OK.
All right.
All right, so after we talked about computational thinking, after we talked about Scratch, the next week we transitioned to a more traditional programming language, a text-based programming language called C. And our very first program looked something along the lines of this. And when you first saw this, if you were new to computer science, this might have looked a little bit cryptic, where the key of things was really just hello world. But now that we have a better understanding of computer science, now that you've had an opportunity to write some more programs, we can really try and get an understanding for what this entire program is doing and what each of these different parts means. So up here at the beginning, we had include standardio.h. And anyone remember what that line of code did? Like, why did we need this line of code in our first very simple program? Yeah, it's a library that contains, in particular, mention of this function called printf, that later in our program, we're going to run this function called printf to try and print out hello world to the screen. And we don't care exactly how printf takes care of actually putting each character in the terminal screen. But we do care that it's able to do that, and we care that we're able to use it in order to do that. And so printf here is a function. It's an abstraction. We don't care about the low-level details of how printf itself is implemented. But inside of standardio.h is this declaration of, OK, there is this function printf. Here's how you're going to use it. And now we have the ability to then use it inside of our program. Then underneath that, we defined a function called main. We saw that it took as its arguments, like the input to the main function, void or nothing. And that's going to change once we get to command line arguments in week 2. But for now, our program doesn't need to take anything as input on the command line. And the return type of the function, because remember, the first thing right before the name of the function is the function's return type. The return type right now is int. And why might main have a return type of int? What use does that give us? Looking ahead a little bit, we didn't actually talk about this in week 1, but now that we're looking at the program again, we can maybe try and glean it. Yeah? Yeah, so if the program encounters a problem, maybe we want to handle that in a special way. And so generally, this integer that main returns is called its exit code. And if everything goes OK, the program went successfully, the program will usually exit or return the number 0, where 0 just signifies, everything went all right. But if something went wrong, some problem occurred in the program, either it was used the wrong way or it ran into some other issue, you might return some different number, some non-zero exit code to mean something didn't quite work here right. And you probably did this multiple times throughout problem sets where you would check the command line arguments and make sure that they're valid. And if they're not valid, you might display an error message, but also return some non-zero exit code to mean, OK, something didn't quite go right here. Or if you were doing error checking and you tried to allocate some memory, but you didn't actually end up getting access to that memory and it was null, there might be another case where you might want to handle that error appropriately. And so this int, although we didn't talk about it a whole lot at the time, allows us to do this, allows us to say, all right, here's why the program didn't quite work, return an exit code if necessary. And then, of course, in the body of the function, we have this printf function. Between the parentheses is the argument, and in this case, we're just printing out hello world, with the \n being what we would call an escape sequence that just says print out a new line at the end of that string. And so hopefully, even if at the beginning this looked a little bit cryptic, now you actually understand what each part of this program is actually doing, why each part is important, and why it's there. And of course, if we look at other languages like Python down the line, we'll find that things get a whole lot simpler. But for now, this gets through that general idea. What questions do we have so far? Yeah?
Why is the exit code useful? What does it work for the program?
Good question. What is the exit code used for? Why do we need it? So oftentimes, you might be curious to find out whether or not a program actually succeeded. A simple example might be to imagine that if you have some script that's running multiple programs, where those programs depend upon each other, you're running one program and then another program. If one of those programs fails, you probably want some way deterministically to know that it has in fact failed. And so one way to do that would be to check the exit code of the program. If the exit code is 0, all right, the program succeeded, we can move on. Otherwise, something went wrong and we can handle that case appropriately. It's just another one of those conventions that makes life easy. If we can all collectively agree that our programs are going to return 0 when they succeed, then that's something that other people can reliably depend on when they're trying to actually run the program. So just a convention that helps us out in certain cases. All right, so we talked about int being a possible return type. But this general idea of types was something that came up again and again. The way that C handles types was a little bit different from the way that Python handles types. Most recently, we saw SQL and the types that come in there when we're trying to decide on types for individual columns. And so C introduced a whole bunch of these different types that we could take advantage of. And in particular, every variable, every piece of data, ultimately had a type. And some of the ones we looked at in the first week were here. We talked about integers for representing numbers. We talked about char for representing a character, like capital A or capital B, which ultimately are really just numbers. We remember the ASCII integer equivalence, whereby the capital letter A is a character. That's equivalent to the number 65. And if you ran a C program that checked, is capital A, the character, equal to the number 65, that program would say true. Those things are the same thing, because the zeros and ones ultimately that represent capital A are the same zeros and ones that represent the number 65. And so we get that equivalence there. Then we had long. And what was long, if anyone remembers? Yeah, a longer integer. So each of these data types that we're talking about has some fixed finite size, some number of bytes that we've given to store the value inside of this variable. And conventionally on CS50 IDE and most of our machines nowadays, a typical int is going to be 4 bytes, or 32 bits, which allows us to store numbers in the range from like -2 billion up until +2 billion. But if you wanted to store a number outside of that range, for instance, you might need some bigger data type. And a long, for instance, generally stores 8 bytes worth of data in order to store an integer, which just drastically increases the number of possible values that we can actually represent. Float, meanwhile, was used when we didn't just have like an integer number where we had a decimal, like 2.8, for instance, something after the decimal point that we wanted to represent. And double was the same idea, that if float generally stores 4 bytes worth of data, a double can store 8, adding some additional information or more bits with which we can use in order to try and represent that data. And then strings were introduced in the first week, and we looked beyond that abstraction later on in future weeks. But for now, strings were this idea of representing sequences of characters. That if we had some text, a name, for instance, that could be used as a string. And then finally, Athena talked about Boolean expressions earlier. We talked about this idea of Boolean values, about things that are true or false, and expressions that evaluate to either true or false as well. So these were some of the basic types that we're thinking about, and each one of them serves a slightly different purpose. Questions about types, in C at least? Yeah?
So in Python, you don't declare data types while declaring variables. So in C, you do declare the data types. Is there any advantage over the two? Like, is there an advantage if you declare a data type is better?
Yeah, great question. So the question was, in Python, later on, we saw a language that didn't require you to declare types, where you could just say x equals true, for instance, instead of like bool x equals true, or instead of like char c equals capital A, just c equals capital A. You could do things like that in Python without having to specify the type of something. And so thinking in terms of our themes for the semester, like what are the trade-offs there? What are the advantages and disadvantages of one over the other? Anyone have any ideas? There are many possible answers here, but why might we prefer to have a language like C in which we're being very explicit about the types of everything, and why might we prefer to have a language like Python where we don't specify that? Yeah?
The benefit of C is that it allows you to be super precise, both with like memory allocation and also this example with exactly how much space you want each data type to take up, and yeah, how you want to use the one specifically. Whereas Python, you don't have that same control, but it's a lot more powerful than C. You can do a lot more things quicker and easier and more possibly sensibly given function language and stuff.
Yeah, so C allows you to be very precise about what it is that you want. Great, that if I only need 4 bytes for my integer, I can use an integer, and I don't need to use a long if I don't need that extra space. So it allows me to be very precise about what we want, only get the amount of memory that I actually need. Whereas in Python, all of that is abstracted away. When you declare a variable, you don't need to know how many bytes worth of space it's taking up on your machine, for instance. But the disadvantage is, or one of the advantages of Python therein, is that you now have the ability to do things a little more quickly from the programmer's end, that you don't need to spend the time thinking about bytes. Just let Python take care of all of that for you. So that's definitely an advantage there too. Another one to maybe consider is that in C, if your types don't match up, what would happen? If you tried to assign a string, for instance, to an integer, what would happen? You get an error, and you get specifically a compiler error. Like your code wouldn't compile if the types didn't quite line up, meaning you couldn't even run your program unless all of the types matched up, unless everything type checked, so to speak. Whereas in Python, if your types don't quite match up, if you're trying to add a number to a string in a way that you're not supposed to be able to in Python, the program will still like compile, so to speak, though it means something slightly different in Python's context. Like you'll still be able to run the program, but when you do at runtime, you'll get an error. You'll get some error that says, sorry, you can't add together the string and the number. And so C will let you check for some of those kinds of errors before you actually run the program, such that you can eliminate certain types of bugs altogether before the program is actually running. So another one of those trade-offs to consider. Talk about variables?
Variables. Cute. Alrighty. So once we have this idea of types, we can immediately start using them. And you guys might remember this, where we were doing things like hello world, but making it a little more interesting, where maybe now we're asking, we want to say hello to our user. But we need to be able to store the name of our user. So we have this, nifty function. And just as a quick recap, how are we getting access to this function? It's actually not on this slide. Right, the CS50 library. We needed to be able to reference this function. We needed to know where this was defined, how it was defined, so that we can use it. We would have included the CS50 library. But here what this function is doing, and again, we don't know how it's doing. That's been abstracted away for us. But what it's doing is it's getting input from the user, right? The user is going to enter their name in the form of a string. And now we have this string, but we need some way to be able to store it and then use it elsewhere. And so we have this idea of variables, right? Where these are things that we have given names to, and by virtue of giving them names, we can now use them again elsewhere. But they also have types associated with them. And as Brian sort of mentioned here, the considerations we take into account when we're declaring variables and declaring their types really alters what our program is doing. And the question you always have to ask yourself is, well, am I using the right amount of space and memory for this? Am I using the right type for this operation, this variable? And so in this case, we're using string because what we expect to get back from getString, a very appropriately named function, is of course a string. And so now every time our program is going to see the variable answer, it's going to know to interpret it as a string. And that becomes really useful elsewhere if we ever pass answer to another function that is expecting a particular data type, or in this case here where we're actually using like a placeholder, right? We're using this %s. If we'd used something like %i, what sort of error might we have gotten? I don't know if that was a hand back there. So as a quick reminder here, these placeholders really needed to correspond to the data type that you were giving them. %i was this placeholder for integers. So if we had used a %i placeholder here and then passed it a string, is a string an integer? No, right? It's not. We're going to get a compiler error here where our types are not matching. And so at the end of the day, what we're caring about here is saving our data, but saving it in an appropriate format. And so this goes back to this theme of like, how are we representing our data? What choices have we made in representing our data? You wanna?
Sure. Some of this stuff Athena already talked about when we talked about Scratch, but we talked about the idea of using conditions. So we saw ifs and else. This is something that came up again and again. I'm not going to spend too much time on it because this is hopefully syntax that you've seen before, that you understand what it is that this logical flow means. We saw another type of syntax with regards to loops. So instead of Scratch's like repeat 10 times, we had for loops, whereby we would initialize a counter variable I, set it equal to 0, run through the loop. After every time we run through the loop, we say I++, or increment I by 1, and then do a check. Is I less than 10? And we're always doing this check before we do every iteration of this loop to say, is I less than 10? If it is, then keep running the loop. But as soon as the test condition fails, then we're no longer going to keep running the loop. And we saw different types of loops as well. A while loop that will just keep repeating the same sequence of statements so long as some condition is true, some Boolean expression is true. And then likewise for a do-while loop, where the only difference between a while loop and a do-while loop is that this do-while loop, this section of code is guaranteed to happen at least once. Whereas in the while loop, if this condition is false, the code might never happen. In a do-while loop, you're always going to go through the code once before you do the condition check to see whether or not the condition is actually true. And there are cases where that might be a more appropriate solution. You might have used something like this when you were getting input in some of the early problem sets, for instance. But as you might think about looking forward in the course, languages like Python, for example, they have for loops, although the syntax is a little bit different, and they have while loops, but Python doesn't have a do-while loop. And so in order to implement do-while loops, we had to use some of the other language constructs within Python, so using a while loop, for instance, plus some way of breaking out of that loop in order to implement the same functionality that a do-while loop gave us. And so even though Python didn't have a do-while loop built into it, using the language features, we were able to build that same behavior out of it. So you can look to the lecture examples for how specifically that happened, but just know that that was one difference and one thing we were able to use. Yeah?
One thing that I always like to talk about when I'm explaining loops is that we use specific loops for specific things. For loops are really great if you have an idea beforehand how many times you want that loop to run. If I know that I want this loop to run exactly 10 times, do I really want to use a while loop? Maybe not. I can just use a for loop and set my condition appropriately. On the other hand, while loops are really great if you don't necessarily know how many times you want your loop to run, but you want to be able to check some condition to know when to break out of it. So this idea of like, do I know beforehand what I need to be doing and how many times should maybe help influence your design decision in, do I use a for loop or a while loop? And of course, do while loop kind of fits under this while loop idea.
Yeah, great point. And in fact, when did this come up? If we think about our problem sets, for something like Caesar, for instance, where you were going through every character in your input and just trying to encipher each one of them, that was probably a for loop, where you're saying for each character in the sequence of characters, you know the length of the string, and you're just going one character at a time, encrypting each one. So for loop probably makes sense there. Whereas in a case like recover, for instance, where you don't know exactly how many chunks of data you're going to be reading from this file, you're just going to keep reading chunks until you get to the end of the file, that might have been a better case for a while loop, whereby it might have made more sense to just say, as long as I can keep reading data, let's do something with that data and try and check to see whether it's a JPEG file or not, for instance, even though you might not have known at the outset exactly how many times that loop was going to run. So definitely design decisions to be considering there. And design decisions are yet another one of the themes, although not explicitly listed, of the course, about thinking about what's the right choice of language, the right choice of tool, the right choice of language feature to use in particular situations, and choosing the right one for the right situation has been one of the big themes of the class too. We then talked about functions. We talked about functions a little bit already, but with this function taking some input, providing some output, or void in this case to mean providing no output, no return value, and then doing some particular operation. This was one of the first functions we wrote in week 1, but you've been writing functions in this most recent problem set and writing functions throughout the semester as well. But the key here is the encapsulation of particular behavior, abstracting it away such that someone using the function doesn't need to care about the behavior. They just need to care what input to provide it to the function, and they can reliably expect what output they should be getting from the function. And so that allows us to be able to build upon these functions. And we used functions that other people wrote because we knew what input we could provide and what output we would get as a result. Yeah?
Why isn't it main void? Why is it just void?
Why is it?
Why isn't it main void?
So the main function, why is it int main void? The int as the return is the return type, signifies the exit code, in other words, like whether or not the program succeeded. And so if everything went well, the program exits with a status code of 0, meaning everything was OK. And if something went wrong, generally the program will exit with some other number, such that you can then check what the return value of the main function was. If it was 0, you know the program succeeded. Otherwise, you know something went wrong.
Yeah.
Why isn't this function?
So in this case, when we're talking about int main void, we're actually declaring a new function called main. In this case, we're declaring a new function called cough. Maybe we use cough in main, but main itself is a different function from cough. Like these are two completely different functions, and as a result, we're not using main here. To be clear, main is not like a special keyword in C that corresponds to like this program that you're running. It's just another convention where typically we put the main logic of our code into the main function. But you could call that function foo if you wanted to, or llama if you wanted to. The idea here is that you're being consistent in how you're calling and naming your functions. Did that answer your question?
When you do compile and run the C program, though, the main, although main is just a function, the main function is what we might call like the entry point to the program, where that is the function that is going to be called first. And so any of the other functions that are called within main, those functions can exist separately, but main is often the one calling them, and other functions can call other functions as well. And we'll talk about that a little more when we get to the stack. OK, now where can things start to go wrong? Do you want to talk about floating point imprecision?
Everything goes wrong. Yeah, so what we're looking at here, as humans, when we do division of things that are fairly simple, like 2 divided by 10, we have this idea of what it equals, right? We know it's going to equal 0.2, and there's nothing else after it. However, there is stuff that comes after that too, right? There's this infinite number of zeros. But as we're dealing with computers, we have a finite amount of memory, and as a result, computers can't represent that infinite number of zeros. So they do the best they can. And we have this idea that, OK, well, it's going to be pretty precise up until a point, and then it's going to start filling in these like garbage values. So as you can see here, we were like nice and precise right until about there. And then the minute we got past there, we started getting these random values that really don't mean anything. And as a human, we look at that and we say, OK, that is definitely not equal to 2 divided by 10. This is this idea of this floating point imprecision, which boils down to a memory issue, right? Where computers have a finite amount of memory, but if we try to represent floating decimal points that could potentially have an infinite number of numbers after the decimal point, computers just can't represent it as precisely as we want without starting to use larger and larger data types.
I'm just remembering I used to do computer network security, and one of the things that the standing joke was 2 plus 2 equals 4, except with extremely large values of 2, and that's where it came from.
Yeah, the joke here was 2 plus 2 equals 4 for extremely large values of 2. Except extremely large values of 2. All right. Other things that could potentially go wrong, one is integer overflow. So we talked about this idea of, all right, an integer is generally 4 bytes large. It can store numbers from -2 billion to +2 billion, or approximately. So what happens if the integer gets too big? What if you get to the biggest integer, and then you try and add 1 to that? Well, the computer is not going to be able to represent that larger number. And so what we get there is something called integer overflow, whereby that number might like wrap around, and you might end up getting like a really big negative number because you've exceeded the boundaries that the computer can represent in 4 bytes worth of integer memory, and it ends up going to a large negative value.
I have a great analogy for this. I'm all about analogies. Some of us in this room are probably too young for this, but have you guys ever looked at like an odometer on an old car? These used to like just roll over as you drove mile after mile after mile, but they were finite. And so if you ever got to like 99999 and then drove 1 more mile, it couldn't just add another digit there, right? Like this was a physical thing in a car. It wasn't just going to magically come up with another value. So what it did is it actually rolled back to all zeros, and that's exactly what's happening here.
So another thing to definitely be aware of as well. And so that was sort of the general idea of the C lecture. We talked about how it's interacted with other languages. We've talked about abstractions and things that can go wrong. But with just C, what questions do you have? All right. We'll pick up the pace a little bit since we have the rest of the semester to get through. But let's go ahead and move on now to week 2. We talked about arrays. We're talking about memory management. And so the first thing we talked about in week 2, actually, before we got to arrays, was this idea of like compiling our code. Like what happens when we take our C program and try to run it? Because our computers only understand zeros and ones, but our writing of code, we're not writing programs by typing zeros and ones on our keyboard. We're writing it by writing C code, some syntax that looks almost English-like or that has English-like keywords that the computer doesn't understand natively because it can only understand zeros and ones. So what does that translation process look like? Well, the command we ran looked something like this, where we were running Clang, which is the name of a compiler for C language compiler. We were generating an output file, -o hello, called hello. That was the name of the program we would actually run. What was the name of the program we were compiling was something like hello.c. And then this -l CS50 was saying, let's link the CS50 library, because maybe hello.c is using the getString function. But the getString function is not a function that I wrote. It's something that the CS50 library wrote. And so somehow the program needs to have some knowledge of that getString function to be able to use it. And so what are the steps of the compilation process of going from source code, our C-level code, down to machine code, the zeros and ones that our computer actually understands? Well, we boiled down this process into generally 4 steps. The first step was called pre-processing. And so pre-processing happens before the actual compiling happens. And it's a simple step that's looking at things like the hash include standard.io.h. That line, hash include standard.io.h, is what we technically call a preprocessor directive. And what that line of code is saying is tell the preprocessor to just take the contents of a file called standard.io.h and literally place the contents of that file right at that point in the file. It's as though we had taken standard.io.h and almost copy-pasted it into the top of our file, such that we get all of the function declarations, the declarations of functions like printf, such that later on in our program, if we ever use the function printf, C doesn't complain and say, wait a minute, I don't know what that word means, because it saw further up in the code that we inserted via the preprocessing step that, oh yeah, printf is a function, and now we can just assume that it's a function that takes this type of input, and we can then use it appropriately. So that's preprocessing. The compiling step, interestingly enough, in the process of compilation, there's a step called compiling, which is a little bit confusing. But the idea there was take the C language source code and convert it into a lower level language, a language that is a little closer to the machine, that would be annoying to actually write code in nowadays, but is just a simpler set of instructions. And that language is called assembly. And there was a brief slide on it in lecture where you saw there were instructions like add this number to that number, or move this piece of memory to that piece of memory. And in assembly language, there's only a very fixed set of types of instructions. You can add things, you can move things, you can jump from one instruction to another, and a couple other operations. But you don't have the fanciness of do-while loops and while loops that C has. You have a much smaller set of features. And we do that so that in the next step, called assembling, there's a very simple translation from any instruction, like add or move memory, to the binary sequence of zeros and ones that actually represent that program. That there's a sequence of zeros and ones that represents add this number to that other number. And assembling is the process of taking that assembly language, that assembly code, and converting it into the zeros and ones that actually represent it, something the computer can understand. And then finally, the last step, now that we have these zeros and ones, we need to link our program with any other binary zeros and ones that our program needs in order to run. So if we are running the printf function, for instance, we're also going to need access to the zeros and ones that tell the computer how to run the printf function. Or if we have the getString function that's not in our program, we need to combine with it the zeros and ones that actually run the getString function, for instance, linking those binaries together such that the result is the machine code that we can actually run on our computer. So all of this was actually happening when we were running Clang, when we were compiling our code. but we didn't have to worry too much about it, but it's good to understand that these steps are in fact there. What questions do we have about compiling? Yeah?
So you talked about how during preprocessing we take the contents of the libraries that you imported, were included, and you just like put it all there. So would that mean that if you're including a library to say implement one function, is there now like a benefit and drawback to implementing libraries in terms of space and speed of your program?
Oh, good question. So the question is, all right, if I'm taking the entire contents of standard.io.h and in the pre-processing step, just sticking it at the top of the file, isn't that going to make my program a whole lot longer? It does, in fact, make the C source a whole lot longer for just that pre-processing step. But then in the remainder of the steps, when it's compiling things down into like the instructions that are needed, if we didn't need those previous function declarations involved in the specific instructions, then later steps are just going to ignore that previous information. So the machine code that we get at the end is not going to be like all that much larger. So it's not actually all that large of a concern. But it's a good point and good thinking about the types of trade-offs that might come up. All right, so in this process, we took C code, then we run it. When we run our code, things don't always go the way we expect it to go. So one of the skills we teach in the class is debugging. And Athena, do you want to talk about debugging strategies?
I love debugging.
OK.
All I do is debug. OK, so a few tools that we gave you guys. We're looking at things like help 50, printf, and debug 50. Help 50 was this tool that we gave you when you're writing your C program. It's the first time you've ever really dealt with this. And now all of a sudden you have a compiler error. Wouldn't it be nice if compiler errors were intelligible? Well, yeah, it would be great, except that they're not. And so as a result, Help 50 is really there to help you get an idea of what those sometimes obscure compiler errors mean. Sometimes these are things like, uninitialized variable or like unused variable. And sometimes they make a little bit of sense, but other times you get very weird errors that are a little bit difficult. The idea with Help 50 is not to be the solve-all catch-all for your compiler problems. The idea behind Help 50 is to sort of teach you to teach yourself what these errors mean. So maybe the first 5, 10 times you see the error, you run Help 50, and then the next 20 times you see the error, you say, oh, I remember what this was, I can fix it very quickly. However, sometimes you don't get errors in your compiling, right? Sometimes you get errors in your logic, and that's where the debugging process starts to get a little bit more in depth. There's sort of two methods of debugging that we teach in the class. There's printf debugging and there's debug 50. Printf debugging is a really great way for you to see how far your program gets. What's the value of a variable at this particular line? And the way we're doing this is by literally inserting printfs into our code, which doesn't change really the logic of our algorithm. It just is giving us this side effect of printing something to the screen, but it's letting us see as a human what our code is actually doing. Debug 50 really takes that one step further and lets you do that for your entire code, letting you set things like breakpoints, saying things like, OK, code, run until you hit this point, stop, and now let me inspect what's actually happening. So you might inspect values of variables. You might actually step into functions, which lets you then step line by line through the function to see if it's doing what you actually expect it to do. Once we got to Python, we still have this ability to use fancier debugging tools, but always keep in mind that print debugging for Python, printf, and C, always a valid way to start debugging your code, at least to get an idea of what is going on. Questions about debugging? OK.
Arrays?
Love arrays.
All right.
You have the clicker.
Oh, sure. Go for it.
Cool. Arrays. All right. So arrays were sort of like first data structure that we talked about. How quickly should I go through this? I know
Go through it. I'm assuming hopefully arrays are something that you've seen before, that you're getting pretty comfortable with. So we'll talk about them at a high level.
OK. High level, yeah. OK. So arrays were great. Let me step back. Variables were great if we had one instance of that variable. Let's say that I wanted like 10 ints. So one thing I could do is definitely go, OK, like int n0 equals this, int n1 equals this, all the way up to n9. Sure, I can do that, but that gets really out of hand really quickly, is not great design. Arrays are really great because they help you encapsulate data of similar types. So specifically, what I could be doing here is saying, OK, well, I've made this int, and it's called value, and I've stuck the number 28 in it. But what if I want multiple values, right? And so you guys hopefully remember the syntax where we're saying, OK, the type in my array is going to be int. So this like analogy of declaring the type first still holds true even when we're talking about arrays. We've given it a name, just like we used to give value a name. But in this case, we had to be really careful to specify the size of our array. And this went back to what we were doing with memory, right? And as we talked later in the course about linked lists versus arrays, this was one of these trade-offs that we talked about. Because, you know, once we specify the size of this array, can it grow? No, right? Once it's of size 5, it is going to be of size 5 forever. However, I can very easily access it, right? We have this random access memory where I can say, okay, go immediately to index 0, go immediately to index 4, and I can immediately get the data stored at that index. And, well, can I just get like a poll? Was that too fast? No, was that okay? Okay, awesome. Cool. So we can just go through this. As I'm clicking through this, if you see something that is not what you expect it to be, I don't like the clicker. My goodness. Okay.
And then, if I could just interject
Yeah.
for a moment. So we've created an array of 5 values.
Yeah, I know exactly
And
what to do.
we've put 10 in the first slot, 20 in the slot 1. And recall that the index numbers start at 0. So value square bracket 0 is the first thing in the array. We put 10 at index 0, 20 at index 1, 40 at index 3. What if I tried to access like value square bracket 2? What's there?
Junk. Junk was the answer, right? Again, finite memory in your computer. This memory was probably used for other things previously as your computer has been alive. And as a result, there could just be garbage values there, right? So if you try to then use, you know, values at 2 in your program, expecting it to be something that A, will work and that B, won't crash your code, you're kind of gambling here a little bit. But that is worth noting. Okay. Is that what
Yep.
you wanted for this slide?
Yep.
Cool. Yeah, I realized I missed it and I was going back. Okay, so when we talked about strings initially, we then kind of took off those training wheels and said, surprise, they're not strings. They're actually arrays of characters, right? And this sort of makes sense. You know, a name at the end of the day is just one character after another. And since arrays are really good at grouping together data types of similar types or values of similar types, it makes perfect sense that we would then think of strings as really just these arrays of characters. So this string Zamila is really just, or rather, the string Zamila, which we saved in name, is really just this array of characters that is the length of Zamila, but not quite. What else is happening here? Let's see if it fills it in. Of course it filled it in. Yeah.
No.
Right, we have this null delimiter at the end. And the reason we do this is the following, right? In memory, if we're just kind of sticking strings next to each other, we need some way to know when one string ends and another string begins. And by convention, we have chosen this null character to mean the end of a string. That being said, if I ever called something like strlen on this string, what is the length of this string? Quick counting, right? Yeah, 6, exactly. It doesn't include the null terminator because that is not actually part of the string. Okay, and if we remember again that this characters themselves really are just abstractions away from numbers, right, and away from these zeros and ones at the end of the day. So Zamila, if we took away this ASCII abstraction, is really just these numbers. And you know, I don't memorize ASCII, but I do remember that lowercase a is 97, and we see that popping up here. And we see that this 0 is, the null terminator is actually represented as a 0. So that was fast, hopefully not too fast. Questions about this before we move on? Yes?
How do you know if it's like put a garbage value or null value in the extra box for like the previous slide?
So how do you know, let me make sure that I understand your question. Was the question, how do you know that you're going to get a null terminator there and not a garbage value? Is that the question? Yeah, so that's a good question. Actually, do you have an answer to
Yeah,
that?
so when you have a string literal in C, like double quote Zamila, the way that C translates this in terms of storing it is it will take care of putting the null terminator in there for you, such that you don't need to worry about it if it's in double quotes. But if you're doing something like copying a string from one array of characters to another, then you're manually doing the transfer. You want to be careful to actually transfer the null terminator terminator on your own, because you are the one actually putting memory in that location. And you're absolutely right that if you forget this null terminator and there are potentially garbage values here later on, that could cause problems in your program in one way or another.
That's a good question. command line.
All right. Command line arguments were another thing that we talked about in week 2. So this was another way of trying to provide information to our programs. So we started with simple programs, like running just /cache might have been a program you wrote in week 1, for instance. You run /cache, you run your cache program. But then we also saw programs like make, where make was a program that ultimately was using Clang to help compile our program. And we ran a command like make Mario. How many command line arguments are there in this program? Or if you think of that things in the C sense, what would argv be equal to? The number of command line arguments. Yeah? 1, there's one argument here, Mario, although technically what will argv's value be? 2, yeah. There's Mario, yeah, this is the one additional one. But there's actually still make and Mario. And you might imagine that a program might want to be able to check both of these. And so we call this, OK, argv is going to be 2 in this case for 2. Argc, sorry, not argv. Argc for the count of the number of arguments is going to be 2 instead of 1. And then what about for this example? Clang-o hello hello.c, compiling the program hello. What is argc, argument count? Yeah, 4, great. 1 Clang, the -o is another one for a second one, hello hello.c, for a total of 4. So how do we actually use that information? Well, inside of our program, we might have had code that looked something like this. Rather than int main void with void in parentheses, we might have had int main and then these 2 arguments, int argc for the count of the number of arguments, and then argv for argument vector, which is really just going to be an array of strings in this case, where this is an array where argv0 is going to be the first command line argument, so make or clang or cache, for instance, and argv1 is going to be the next argument that was provided to it. And we can find out how many arguments there are using argc. And so this was a way of providing additional information to our program at the point at which we're running it on the command line, where you might have been running /Caesar, running your Caesar program, passing in the key, the amount that you wanted to shift the program by. Or in recover, for instance, you might have typed /recover followed by the card.raw file, the name of the file that you wanted to recover images from. And so we were able to use command line arguments in that way, both in your own programs that you were writing, but also in programs that you've been running throughout the course of the semester. So like check 50 or submit 50, for instance, takes as its command line argument the name of the problem that you want to check or submit, for instance. If you've ever used like cd to change your directory into something else, yet another example of a command line argument. Yeah?
So if argc is 2, when that prints out, does it print out as 2 or does it print out as 1 because it starts counting?
So the question was like, since the string starts counting at 0, like how does the value of argc compare to that? If argc is 2, that means that there are going to be 2 arguments that are passed in, one of which is stored in argv0 and one of which is stored in argv1. And so this is another thing to be careful about, are these off by 1 errors that are very easy to make, especially when arrays begin with 0 and might not be initially intuitive, whereby if argc is like 10, you're not going to be able to access argv10. You're only able to access up to argv9 because the first argument is stored in argv0. And so one of those slightly tricky things that you have to think a little bit about. All right, last thing we'll talk about before we take a break, which we'll turn to Athena for, is sorting, which we talked about at the end of week 2. Another example of these algorithms that we were using for particular purposes.
So we had these 3 main sorts that we talked about. If we sort of remember at the end of the day, the goal here is to take an array, typically of integers, but you could also imagine doing this with characters, right? Really anything that you can compare and then order and put it into some order. Usually ascending order, right? Usually we like 0, 1, 2, 3, 4, 5, 6 as opposed to the other way around. And of course there's different ways to do that, and sometimes we have to ask ourselves if one way is better than another. Bubble sort, if you guys can kind of imagine what this looks like visually, and there's a lot of great resources online if you ever want to visualize what these sorts look like. Bubble sort really is asking like, hey, is this thing the greatest? Oh yeah, great, I found the greatest. And it makes this comparison, bubbling up the greatest value until it ends up in its final position. And so at the end of any iteration of bubble sort, you have the next greatest item in the position that it needs to be in, right? Selection sort is the one that I always get wrong. Do you want to?
Why don't we visualize selection sort just to see it for a moment? So selection sort, you might imagine if we were trying to sort 5 numbers like 3, 1, 5, 2, 4. What we're first going to do is like find the smallest thing in the array. We're going to go through this whole thing like trying to select the smallest one. So we're going to start at the beginning of the array and say, okay, 3, this is the smallest thing we've seen so far. And then we move on. 1, okay, 1 is smaller than 3. This is the new smallest thing I found. Let me check. Is there anything bigger than 1, 5, 2, 4? No. All right, so 1 was the smallest one. So where does 1 belong? Yeah, on the far left, if we're sorting things from smallest to highest. And so the first step of sorting might be to take the 3 and the 1 and just to swap their places.
What was next? 5, 2?
5, 2. But we swapped the 3 and the 1. So it should be 1 and then 3. All right, 1, 3, 5, 2, 4. Still not sorted, but we've made some progress. And so then we do the same thing. We know that 1 is sorted, so let's just now sort these remaining 4. 3 is the smallest thing we've seen so far. Let's see if we can find anything smaller. 5, okay, that's not smaller. 2, that is smaller. 4, all right, 2 is the smallest thing we've seen so far. So we can take the 2 and the 3 and just say, all right, let's go ahead and swap those 2. Now the first 2 are sorted, and we just have to worry about sorting the remaining 3. And all right, find the smallest thing, 5, 3, 4. 3 was the smallest one we found there, so we can take the 3 and the 5. 5, swap those 2. Now the first 3 are sorted, and then the last step, all right, check here. Smallest one we've seen is 4, so we can take these 2 numbers and say, all right, swap those. 4 goes there, 5 goes there. The last time there's only 1 number, and so we can be confident that this whole array is now sorted. And we did this just algorithmically, step by step, of saying, all right, go through the whole thing, find the smallest thing, move it to the beginning. Take everything remaining, find the smallest thing, select it for selection sort, move it to the beginning, so on and so forth until we made our way through the entire array and sorted the whole thing.
Yeah, okay, great. And if you can, thank you. Right. And finally, the last one was merge sort. So merge sort was this idea where you started with something that was unsorted and you broke that problem in half again and again and again. If you guys are ever like, yeah, I know, maybe I'm not going to make that analogy. Right? You're breaking the problem in half again and again and again until you end up with smaller units, usually each one of 1 unit, and then you start recomposing them. And as you recompose at every step, you are ending up with something that is more sorted than what it used to be. So if we visualize this again, great, and it's already there. Great, so if we broke this in half, we can kind of imagine, well, this doesn't break in half super nicely, so let's already sorted.
Let's do a non-sorted one.
Okay. Like, wow, that was an 8, 9, like 2, 1, and okay.
Let's add one more number there.
Yeah.
For, 4.
Yeah, 4 is a great number. What a great number. 4 is a great number. Okay, so if we kind of imagine splitting this in half, right? So now we have these 2 arrays now, both of values, right? And we split in half again. Admittedly, this doesn't split super nicely, but if we split, we might end up having like, okay, there's 4 and then 8 and 1, right? And here's this new split.
9.
If we, oh, this was an 8, this was a 9.
That's a 9.
That was a 9. And then if we split this one again, you can imagine that we have now this like 8 and this 9, right? And what's confusing about merge sort is not so much this like idea of splitting things again and again, but is this idea of how am I putting them back together? Why is the idea of putting them back together actually sorting them? And the question you're making there, or the question you're asking there is, okay, each of these you can kind of imagine is an array of size 1. And really what I want to do is put them into an array of size 2. So the question I'm going to ask myself, like if I had 2 hands, I'd compare my 2 hands and I'd say, okay, which one of these 2 values in each of my hands is smaller in this case, right? And in this case, what I'm going to do is say, okay, 8 is definitely smaller than 9, so I'm going to go ahead and put it there. And I'm going to look at my other hand and say, okay, great, 9 is definitely bigger than 8, and I can go ahead and put it there. Now the next comparison I'm going to make is between this array of size 1 of 4 and this array of size 2 of 8, and the size that I'm trying to make it now is a new array of size 3. And I'm going to do the same thing, right? I have my left hand holding 4, I have my right hand holding 8, and I'm going to say, okay, which one of these 2 is actually smaller? Oh, 4 is definitely smaller. I'm going to go ahead and put it in there, but now I still have my right hand here, right? My right hand can say, okay, great, since 4 was smaller, 8 must be the next biggest, and 9 must be the next biggest. And this idea kind of propagates back up as we go through each level where we had split it in two, until finally we end up with a nice sorted array at the very end. What is more interesting about these, oh, actually, yeah. Forgot we were.
So fundamental to that idea of merge sort was this idea of like recursion, this idea of, all right, we can break down the big problem of sort the big array by saying, all right, let's first solve a smaller problem, sort the left half of the array, and then sort the right half of the array, using merge sort to sort each half, where each half is sorted by saying, all right, let's use merge sort to sort the left half and sort the right half, which feels sort of weird that we're using merge sort to merge sort a larger array. But the ultimate idea, as Athena was talking about, is once you get down to an array that's only like one element, well, that's already done for you. And so the only hard part is, all right, if I've sorted the left half of the array and sorted the right half of the array, is how do I combine them? And you can do that using the method Athena was talking about.
Yeah. So when we talk about algorithms, the next thing we typically talk about is this idea of runtime or time complexity. And we have this notation here of this like big O and this n squared. Big O you can think of as like a worst case, right? If I have the worst possible input for my algorithm, how long is this really going to take to run? Now, it's important to note here that how long is not necessarily time on a clock. How long is this idea of like asymptotic time, right? So as my inputs get really, really, really big, how many steps, you can ask yourself, is my algorithm going to have to run in the worst case to get me to the output that I want? So in this case, when you're thinking about time complexity, one way to sort of think about it is to ask yourself, okay, at each step of my program, how many like elements am I touching, for example? So in the case of bubble sort, right, you know that you need to make like at least n comparisons, right? As I'm stepping through each one of these items in my array, I'm saying, okay, is this bigger than this? No. Is this bigger than this? No. Is this bigger than this? And I'm doing that for every single item in my array, right? So if there's n items in my array, and I've made n comparisons, this is going to leave us with a runtime of n squared, right? Selection sort is really doing the same thing, right? Every time it passes through that array saying, is this one the new smallest? No. Is this one the new smallest? No. Oh yeah, look, this one's the new smallest. It has asked that question at least n times, right? And it has done that for every element in the array. We end up with this n squared again. Merge sort is kind of the weird one, right? And this is where we start to ask ourselves, where are we getting a runtime like n log n? So when I took this class, I was not super mathematically inclined. And so if you don't know what a log is, don't feel bad. One way that I had someone explain logs to me is to say, okay, if you ever find yourself splitting things in two again and again and again, you can bet that there's going to be a log in there somewhere. And the question is, okay, how many times did I split something in two? At the end of the day, what we ended up doing is we split things down until we ended up with arrays of 1. And so you can say to yourself, okay, I must have split at least n times. So then your next question should probably be, okay, great, so I understand where this log n came from. Where did this n come from, right? Like, what is happening there? That part of the n, and stop me at any point if I'm saying this wrong, that part of the n is coming from putting things back together, right? You're making these comparisons between arrays, but at least you're only making these comparisons once. You're asking, okay, is this bigger or is this bigger? Okay, great, this one. Is this bigger or is this one bigger? Great, this one. You're not doing that for each item, right? Each item, each number of times. You're only doing that once until you end up with this bigger array, right? And you've done that for every time that you've split something in two. And as a result, you end up with n log n. That was the most confusing thing in this class for me when I took it. So how do you guys feel about that?
What questions do you have?
Yeah, yes. Another way of asking that, yeah.
Do you expect the log n more time?
Yeah.
Yeah, so one way to visualize this, if we erase this.
Yeah, I can draw this prettier if you want to talk.
Okay, if we do like 8 numbers, like 1, 2, 3, 4, 5, 6, 7, 8, which don't need to be in sorted order, but 4, 5, 6, let's do 2 more, 7, 8, perfect. So we're trying to sort like 8 numbers. The first step is going to be to break it up into 2 arrays of 4. If we're trying to sort 8 numbers, we're going to sort the left 4, and then we're going to sort the right 4. And okay, how do we sort an array of 4? Well, using recursion, we're going to say, okay, let's sort the left 2, and let's sort the right 2 for each one of those. And we're going to do the same thing on the other side. Sort the left 2 and also sort the right 2. And then how do we take the 2 and sort them? Well, we're going to sort the left half, just the left 1, and sort the right 1. And so the general idea of merge sort is this idea of, okay, break the problem into half and half, take each subproblem, break into half and half, until you can't break the problem in half anymore, until you're just left with one. And then you start to reconstruct things, put things back together. And so the question of the log is, how many times did I have to split something in half? And the idea there is, okay, so if we have 8 inputs, well, log base 2 of 8 is 3. In other words, we're like splitting things in half 3 times. Split in half once, split in half twice, split in half 3 times. And you might imagine if I doubled the size of the problem, I have to sort 16 numbers now instead of 8. That just really adds one additional split that I need to do. Take the 16, split it into 2 arrays of size 8. I know how to sort arrays of size 8, and then we just combine the 2 to form the array of size 16. And so that's where that logarithm is coming from. Great question. Other questions? OK, other questions about anything we've talked about so far? Yeah? The bubble sort, sure. Let's erase that. General idea of the bubble sort, let's do a small one. 3, 4, 1, 2, is to have numbers, the big numbers, like bubble their way up to the top, where we're going to take each numbers in pairs. Say, OK, 3 and 4, are those in the right order relative to each other? Yeah, they are. 3 is less than 4, so that's fine. We move on to 4 and 1. Are those in the right order relative to each other? Well, no, they're not. 1 is less than 4. So we're going to take the 1 and 4, and we're going to switch them. So we get 3, 1, 4, 2. Then we take the last 2, 4 and 2. Are those in the right order relative to each other? No, they're not. 2 is less than 4, so we swap those 2. We get 3, 1, 2, 4, and that's the end of one iteration. We've made it all the way through the array, and the result of it is that the biggest number, the 4, has bubbled its way up to the top. And then we're going to keep doing the same thing again. 1 and 3, well, those are in the wrong order. Let's switch those. So we get 1, 3, 2, 4. And then we're running out of space here, but the last switch is going to be, all right, take the 3 and the 2. Those are in the wrong order, swap those. And then if we were to do that check again, all the numbers are in pairwise order. And if every pair in the array is ordered correctly, well, then the whole array is ordered correctly, because everything from the beginning up until the end is less and then more and then more and then more and then more than that. And so you can actually try these on your own. I encourage you to do so just to visualize it to get a sense for it. Other questions? All right, what I thought we'd do now is take like a 10-minute break or so. There's some snacks of fruit and muffins outside if you'd like them. At about 10:30, we'll reconvene here, and we'll pick up with pointers and memory.
Sad.
Okay, so let's pick up from where we left off. We're now on to week 3, where we were talking about memory. And this is where we started to talk about like how a computer's memory is actually structured, how it's laid out. And crucial to this whole idea was the idea of pointers, which were probably a confusing topic at first. I'll try to distill it if any of it's still confusing, and take questions, of course, as well. But remember that back in week 1, we were talking about types. We talked about, okay, int is an example of a type you can use to represent an integer. Char represents a character. What we introduced in week 3 was the idea of pointer types, where rather than just int and char, we had new types. We had int star and we had char star, where int star and char star don't store integers and characters respectively, but rather an int star is going to store for me the address of an integer, and a char star is going to store for me the address of a character. And so everywhere in my computer's memory, each of those locations has a memory address. And what int star and char star are going to do is they're going to store pointers to those addresses. They're going to store those addresses, an address where I can find an integer or find a character, for instance. So some of the syntax and terminology we needed there. If you declare something of type star, like int star, char star, float star, so on and so forth, that declares a pointer that is going to store in memory the address of something of that type. Then meanwhile, if you do an operation like star x, that's going to take x, where x is a pointer. It's going to go to that address in memory and get the value that's stored there. This is what we call the dereference operator. Star x means go to x, extract the value that's stored there. And then ampersand x means take a variable called x and tell me what address it's stored at. It's sort of the opposite, where star x means go to the address. Ampersand x means get me the address to find out where in memory it's stored. So let's do an example of like walking through what's going on here. When I say something like int a equals 28, what's actually happening inside of my computer when I do something like that is I'm saying, all right, well, I need a variable to store an integer. So here's a place to store an integer. That variable has a name. It's called a. And inside of that variable, I'm storing a value, in this case, 28. But in particular, the one new thing that we're introducing this week, because this is all stuff that you'd seen previously, is that every location in memory has an address. And it doesn't matter exactly what that address is, but maybe it's OX10, for instance, where often these addresses are stored in hexadecimal, those numbers that start with OX something, where hexadecimal is just base 16. And so every location in memory has an address, just a new thing that we were talking about this week, such that if I do something like int b equals 50, very similar idea. Create a variable that also has an address, this time OX14, inside of which we're going to store the number 50. But then if we did something interesting, let's add some pointers into the mix. I add a line like int star c equals ampersand a. What does this mean? What is this going to do? Any thoughts or guesses? Yeah, it's going to store the address of a. So we've got a variable called c. So we're going to create some space for that. This is a variable c. It has its own address too. But what are we storing inside of c? Not an int, but an int star, the address at which an integer exists. And ampersand a means take the variable a, get the address where it lives. A lives at address OX10, so down here inside of C, we're going to literally store that address OX10. And in diagrams, you often see this visualized as like an arrow pointing to A, where that arrow just means inside of C, we are storing an address, and if you go to that address, OX10, you'll find an int. So now if I had a line like star C equals 14, what is that going to do? What changes in this diagram? Star C, recall, is the dereference operator. It means take whatever address is stored in C and go to that address.
So assign 14 to A.
Yeah, so A, which right now is 28, is going to change to 14. And why did that happen? Star C means dereference. OX10 means, and then I go to OX10, here's OX10 in memory, and change that value, instead of whatever it was, to be 14 instead. What if I now said C equals ampersand B? Slightly different syntax. What happens there? What changes? Ampersand again means take the address of something, yeah?
OX10 changes to OX14.
Yeah, OX10 is going to change to OX14. And why did that happen? Well, ampersand B means get me the address of B. B is a variable. Its address is OX14. And I'm going to store OX14 inside of C. So C's new value is OX14. Now let's do one more line. If I do star C equals 20, what changes? The 50 becomes 20. Great. Star C means take the value in C, dereference it, go to address OX14, well, that's right here, and change its value from 50 to 20. And so using pointers, we're able to manipulate values inside of our computer's memory. And the key here is just that something of type int star is nothing more than an address. A pointer is just an address to something inside of our computer's memory. What questions do we have about that? Yeah? A hexadecimal, so the address itself is going to be of type pointer to int. So int star, the type of that means type pointer to int. In other words, C is going to store the address. That hexadecimal address is really just a big number, usually. But we store it in a different type of information, int star in this case. Other things? OK. Let's next then talk a little bit about memory layout. So we have addresses inside of our computer's memory. Now, what's actually stored at those individual locations inside of my computer's memory? Well, you imagine memory as just this like big rectangle of memory. That inside of your computer's RAM, random access memory, you have this whole bunch of space. And that space is divided into different parts. And there are a lot of different parts to our computer's memory. But the two that were really important to us, at least for the purposes of this class, were the stack. And then inside of the stack, what we store are functions, variables, and their arguments. So any functions that we run, the main function, if we have other functions, like in Speller, for instance, we had functions to check whether words are spelled correctly, functions to load our dictionary. Those are all functions. And those functions are going to build on top of each other, forming like a stack of trays almost, where each stack frame represents one individual function. And then up at the top, we have what's called the heap, which stores dynamically allocated memory. So the stack of memory, this is managed for us. As you run functions and as your functions have arguments and variables inside of those functions, you don't need to worry about that memory because the computer will take care of adding things to the stack or removing things from the stack for you. The heap is memory that you ask for dynamically. If you say, I would like an extra 8 bytes in order to store a value of this type, you can ask for memory using malloc, which we'll see in a moment, and that memory you ask for is going to come from the heap, different location where memory is coming from. And as you add more stack space, the stack is going to grow up. As you get more heap space, the heap is going to grow down. And so there is a possibility for like a stack overflow. If the stack gets too big, for instance, you could run into issues there. But this is generally speaking where memory is laid out in a very simple sense. And so you might imagine if we look at this as a diagram, and this is our computer's memory. When you first run the program, you're running the main function, right? So main gets a frame of memory down here. But your main function might call other functions. If your main function is calling your load function, for instance, when you're trying to load your dictionary, then load is going to get its own frame of memory on the stack. It's just going to add on top of the stack. And when load is done running, when you're done loading things into memory, load is done, we're going back to the main function. Then the load function goes away. We're left with just main. And then maybe now we're going to check to see if a word is inside of our dictionary in the case of Speller. So now we're calling the check function. And we maintain this sequence of stack frames, basically all of the functions that are currently running in order of which functions are calling which other functions. And each function has space for its own memory. And so that's that idea of what's going on there. Questions about the stack and the heap and what's going on here? OK. So the next thing we talked about over the course of this week was file I/O, so file input, file output, and how all of that worked. And there were certain operations that we wanted to do on files. We used mainly image files for this week, but it could be any type of files. We wanted to open a file. We wanted to read from a file. We wanted to write to a file, change our position within a file, close files when we were done with it. So this was getting at the idea of cursors that someone was asking about earlier. So what were the functions that we had to use in order to deal with files? All of them were inside of this standard I/O library. But we used functions like fopen, where fopen would open up a file that we had access to. So we use syntax like this, where we had file star foo, where foo is just going to be a variable that it represents like a pointer to that file in our computer's memory. Fopen is that function that's actually going to open up a file. Now, what file do we want to open? some file name.txt in this case. Maybe it was card.raw for recover, or some other image and resize, for instance. And then finally, a file mode. In other words, how are we opening up the file? And there were a couple file modes that we've explored in this course, not only in C, but we saw this in Python as well. The typical file modes are R, W, and A, where R stands for read, if I want to read from a file. W stands for write, if I'm opening up a file so I can write new contents to it. And A stands for append. If I want to take a file and just add new content to the end of the file, I can open a file in A mode to mean I want to append to that file instead. fread, meanwhile, allowed me to read information from a file. So if I wanted to read from a particular file, this file pointer fp, how many blocks of memory do I want to read? You'll pass in as an argument. How much memory goes in each block, like how many bytes worth of memory is going to be specified in fread. And then also, where am I going to store the memory that I've read into memory? You're probably going to store it inside of some area of memory, and you want to pass in a pointer to that memory so that fread can read from the file, take that data, and put it inside of some data structure with which to store that memory. And again, no need to memorize exactly what the syntax or the order of the arguments of fread is, because honestly, that's not the interesting or important part. The idea here is just that we have the capacity to be able to read from files. And you can always turn to the internet or CS50 reference for specifics about what the order of the arguments is. But just getting an understanding and intuition for what these functions are, the fact that they exist and that you can use them, is what's actually important here. We also had fwrite, meanwhile, for writing to a file, which followed a very similar format. fseek, meanwhile, we used when we wanted to move our position within the file. So when we had a file, we had basically a cursor into that file that represented our current position in the file, such that if we were to read using fread, we would read from the next portion of the file. But if we ever wanted to double back, go backwards in the file, or skip over a portion of the file, we could use fseek to do that, to say, move forward 10 bytes in the file, move backwards a couple bytes in the file. So we could do that as well. And then finally, when we were done with the file, we could use fclose to say, all right, we're done with the file. Go ahead and close it. We don't need it anymore. Questions about any of that? How we were able to manipulate files in the class? All right. Other questions before we move on to data structures week 4? All right. So week 4 was all about data structures. Again, going back to this idea of how do we represent data, what are the algorithms we can use in order to manipulate and use that data in some sort of meaningful or interesting way. And this took us all the way back to the beginning with arrays. Right? In week 2, we talked about arrays. We could use it to store contiguous pieces of information. But what were the limitations of arrays? What were the limits that were things that we needed to try to solve? You can't change an array's size, exactly. Once I have an array of like 8 numbers long, if along comes another number, like the number 90, and I want to try and put that in the array, well, too bad. The array is of fixed length. And, there are workarounds. You can try and allocate a bigger array and then copy everything over from the old array into the new array, and that would work. But what we really want are some better data structures that allow us to dynamically grow or shrink the array. And different data structures are better served for different purposes. Every data structure has its advantages and disadvantages. There are some cases where an array really makes sense, and other cases where we might want to use something called a linked list. And so this was the new data structure we saw this week that took advantage of pointers. And so a linked list is going to be a list of nodes. But a node is not a type that C gives us. C gives us ints and floats and booleans and so forth, but it doesn't give us nodes. So we had to define for ourselves what is contained within a node. And we argued that a node, for our purposes, is going to have 2 parts. It's going to have an integer value n, which is just the value that's stored at that node, in the same way that we had values stored at particular positions in an array. And also, a linked list is going to maintain a pointer to another node. The address of another node, and which other node? Well, it's going to be the address of the next node in a sequence of nodes, such that if I have 5 linked list nodes altogether, they'll each point to the next one, such that if I can get to the first thing in the linked list, then I can get to the second thing and the third thing and the fourth thing and the fifth thing, all by following those links. So this is what a linked list node looks like. We've got some value n and some value for what comes next. So then how do we actually use this? If I wanted to ask my computer for some memory in order to store a node on my computer, I might run a line like this. node star list equals malloc size of node. All right, what's going on here? What we get is malloc size of node says allocate some memory. I'm asking the computer for some memory. And how much memory? Well, enough memory to store a node. So that gives me a node somewhere in memory. It doesn't matter where in memory, but it does have an address. And list is going to store what? This variable list is a node star. And node star means it is the address at which a node is stored. So here's my list variable. This malloc size of node, where in memory does that live, the stack or the heap? Let's backtrack for a second. When I malloc memory, heap, great. Heap is where all of the memory we malloc is going to go. It's dynamically allocated memory, memory that I have asked for. List, meanwhile, is just a variable. It's a variable of type node star. In other words, a variable that is going to store the address of a node. And what is the address? It's only one address on the screen. OX280. Great. So malloc allocates some memory on the heap. But that memory is useless to me unless I know where in memory that node actually is. And so what malloc returns to me is the address where I can find that piece of memory that I just asked for. And we're going to store that inside of this variable called list. So this variable called list gets the value OX280, which is going to be a pointer to that node. So now if I want to fill that node with information, I can do so. Yeah, question? Oh, good question. This variable list, where is that stored? Stack or the heap? Stack, yeah. Probably this line of code is like inside of one of my functions. And so list is just a variable inside of one of my functions. And so function arguments and variables, those all live on the stack. So the list variable itself lives on the stack, but it contains within it an address. And that address points me to the heap. All right, so now I want to fill this node with information. And the way I can do that is something like this. List arrow n equals 10 to mean list, follow the pointer, go to the struct, and find the n field, and fill in the number 10 there. And so we'll take list, OX280, go to that address in memory, and fill in that n spot the number 10, filling in some value inside of that node. And maybe this is the end of the linked list. So I don't actually want this next pointer to point to anywhere else. I just want to say this is the end. What value would I put inside of next? Null. Great. Null is this like pointer value that just means not pointing to anything. And so I'll generally say list arrow next equals null to mean, all right, put the value null right there. If I didn't do that, what could go wrong? Segmentation fault, but why? So segmentation faults could happen if we have memory errors, but why might I run into trouble if I don't put something in the next field? And then maybe try to use the next field if I'm looping over a list, for instance. Yeah, it's going to be some garbage value. That before I had null there, this could be anything. And so if ever I tried to say, all right, let me follow the next pointer to go somewhere, well, there could be some garbage value here. Who knows exactly what it is, but it could point me anywhere in memory, and maybe to a part of memory I'm not supposed to touch, which could theoretically give me a segmentation fault. So always good to only use values after you've initialized them. Initialize the next pointer to point to null, such that I can check, is next null, and do something appropriate if so. Questions about this? Allocating memory on the heap for a node, and then filling in that node with values. All right, so here's an example of a larger linked list. Right now, it's just 3 independent nodes, a node with the number 10, a node with the number 20, a node with the number 30. Now I want to string them together. This is actually a sequence of numbers, 10, 20, 30. What goes inside of next here? OX600, great. Because inside of next, I'm storing the address for the next item in this list. OX600 happens to be the address of the next node, and so that's what goes here. Likewise, in this node, what goes here? OX700, great, because the second node is going to point me to OX700. This is the third node. This is the last one. What goes in next? Null. Great. Third one is the end. And so this is a linked list. They don't have to be next to each other in memory. They could be anywhere in memory. But so long as the next pointers are all pointing to each other, the result is that I'm able to reconstruct the list. If I know where the beginning of the list is, I can follow these arrows, so to speak, of going from the first one to the second one to the third one to get all the way to the end of the list. And all I need to do that is some notion of where the first one is. And oftentimes, you can often represent a linked list without visually. You'll often see it without addresses even there, because it doesn't really matter what the addresses are. What's important is that we have these arrows that are pointing me from one thing in the list to the next thing to the next. And so long as I know where the head of the list is, where the beginning of the list is, I can access everything else in the linked list. Questions about any of that? So that was linked lists. It started to give us a lot of capacity. And in lectures and in sections, we talked about how to do algorithms on these linked lists. How do you insert something into a linked list and making sure that those pointers are in the appropriate locations to make sure that we're not losing access to memory, for instance. So I would look back to that for some examples of how to manipulate a linked list, how to add things, remove things. But this was a general idea of being able to store memory in this way. So what are the trade-offs here? Why is this better than an array? You can add things to it beyond the bounds of the array. So the array has a fixed size. Linked list doesn't have a fixed size. I can just add more and more things to this linked list by updating these next pointers and allocating more memory as I need it. What about some disadvantages? Why might an array actually be better in some cases? You can access some random position of the element. Great. Such that if I had an array of size 10 and I wanted to say, get me the 8th element in the list, or in the array, that's a pretty easy thing to do, because if all the elements are stored in order, my computer knows exactly where element number 8 is, and it can jump straight there and get me that value. With a linked list, it's not so easy. The computer only knows where the first element of the linked list is, and the other elements could be anywhere in memory. So to get element number 8, you really need to start at the beginning, go to element 1, then 2, then 3, and go linearly, go through all of the elements up until element 8, and then you can extract it. So there is some time trade-off there, that it takes more time to get to the 8th position in the linked list. What are some other disadvantages? We talked about a time trade-off. What about a space trade-off? Yeah?
Would use more space because they have to have a space to store the number and then a space to store the address.
Yeah, exactly. A linked list is generally going to take more space than an array would, because in an array, what do you need to store? Well, at each position, you just had to store the number, or whatever value you were storing at that position in the array. But in a linked list, on the other hand, you have to store two things. You have to store the address, or the value, and you also have to store the address of the next thing. And in fact, the address might be the thing that takes up even more space than the number itself, because if the number is an int, well, that's just 4 bytes. But generally speaking, nowadays, our addresses are 8 bytes, and so your node might most of the space be just storing these pointers to the next thing in the linked list. And maybe that doesn't matter if you've only got a couple of elements, but if you've got thousands or millions, then it starts to add up. So things to think about there as well. So how do we then use linked lists in order to build larger, more interesting data structures that are more powerful in certain ways, that allow us to do certain things? Well, one of the data structures we looked at were hash tables. And the idea of a hash table was to try to solve one problem, which was to speed up this process of trying to look up information. How can we be more efficient about things? So we might imagine that if I wanted to store a big linked list of numbers, I could use a linked list like this, just to store a whole bunch of numbers. And I might want to ask questions of myself, like, is the number 28 in this linked list in my data structure? And how would I answer that question? Well, I would start at the beginning and say, OK, is this 28? No. Is this 28? No. Is this 28? Well, yeah, it is. There it is. 28's in my data structure. But if I asked a question like, is the number 50 inside of this linked list, inside of this data structure? Well, I'd start to say, is 50 here? I'd have to look through the whole thing looking for the number 50. And maybe I'd find it, maybe I wouldn't. So how could I make this more efficient? Well, one way to imagine making it more efficient would be, all right, let's take this linked list. Instead of making it one linked list, let's make 2 linked lists, each of which is just like half the size. So maybe rather than as I get data, put all of them in one linked list, maybe just, you might imagine the first thought might be, like, let's randomly pick. Let's take the first thing, put it in the first list, next thing, put it in the second list, just keep alternating. Now I've got 2 lists instead of 1. These lists are shorter. Have I made any progress in solving this problem? is it going to be more efficient now to look up things in my data structure? No. People are shaking their heads no. Why not? Yeah, you still need to go through each of these lists because I don't know whether my number is in the first list or the second list. And so the idea of the hash table, or one of the ideas, is to say, if I can deterministically decide, given some input, what list does it belong to, then I only need to check that list and not other lists. So for example, if I wanted to split nodes of numbers up into two lists, what would be a simple way of taking numbers and deterministically placing them into two lists? What? Even and odd. Great. So even numbers go in one list, odd numbers go in another list. Great. So I could do something like this. Rather than one linked list, let's have two linked lists. Let's have a linked list of my even numbers and a linked list of my odd numbers. If a number like 50 comes around, I say, OK, is 50 even or odd? It's even. All right, it belongs in the even list. I put it in the even list. Then what I want to ask myself the question, is the number 50 inside of my data structure? Well, I ask myself, is 50 even or odd? It's even. And since it's even, I have no need to check the odd list. This might have a million elements in it, but it doesn't matter, because I know that if 50 is in my data structure, it's not going to be here. It's only ever going to be in the even list. And so I can check the even list looking for the number 50, and maybe I'll find it, maybe I won't. And so I've cut down on the amount of time it takes to solve this problem in half, basically, because I only need to search half of the numbers that I previously needed to. And so you might represent this in a hash table that looks something like this. A hash table you can think of in this case as just an array of linked lists, where here, rather than one linked list, I have an array of two linked lists. Here's my even list. Here's my odd list. Each one is just a linked list, but I can just decide which linked list I'm going to go to based on my input. If it's an even number, go to this list. Odd number, go to that list. And I've cut down on the time it takes by half. So given that, the logic of the hash table is, why stop at 2? Why not just add more lists, so long as I can deterministically decide which list I should be accessing when I'm trying to look up data? So if I'm trying to store words, for instance, words that start with A's and B's and C's and D's, I might use a very simple hash function to divide things up not into 2 bins, but 26 bins, based on the first letter, where the idea would be, if the word begins with the letter A, then it goes in the first list. If it begins with a B, it goes in the second list. C goes in the third list, so on and so forth. So I end up with a hash table that looks something like this, whereby if I get a word like cat, rather than search through the entire list looking for cat in all of the words in my dictionary, I just have to say, all right, cat starts with C. So if it's in my data structure, it's going to be in this linked list. And I can check, all right, here's cat. And I can ignore the other 25 linked lists. So I've been able to save myself some time. And all of this relied upon what was called a hash function. And a hash function is a function that takes some input and deterministically gives me the same output every time that tells me which of these lists I want to go to, in this case. Yeah?
In the column on the left where you actually like have your letters listed, what does that space contain, like in an actual program? Is it like a pointer to your first node?
Exactly. So the question is, what's actually contained inside of this array of all my linked lists? Each one of these is probably just going to be a pointer, the address, to the first thing in that list. And maybe if there's nothing in that list, then it's going to be filled in with null. But if it's null, you know there's nothing in the list. And if there is a pointer, then it's going to point to the first node in that linked list. And you can follow the next pointers to keep going one after another. So that would be one way to do it, that you could imagine doing it in other ways too. Other things, other questions about the idea of the hash table? So what's the hash function? What was the hash function that I was using for this particular hash table to organize things into different lists, or different buckets, as we might call it? What was I doing? Given some word, how do I decide which one to go, which bucket to go in? First letter, yeah, what alphabetic letter comes first. And so this might be what the hash function would look like. It's a hash function that takes as input my input, some word. And what does it return to me? Well, it's going to return to me which bucket to go in. And the way I determine that is by taking word square bracket 0, first character of the word. Let's convert it to lowercase in case it's uppercase. And then if I subtract lowercase a, recall that lowercase a is just the ASCII representation of the number 97. And so if I take a and subtract a, I get 0 for the first thing in the array. If I take b and subtract a, I get 1 for the second thing in the array. And so by using this hash function, I can take any word and assign it deterministically to a number from 0 to 25, deciding which bucket of my hash table I should put it in. And you might imagine that to make this better, we can make some improvements. Anyone have thoughts as to why might this not be the best choice of hash function? How can we improve upon this? Paul, yeah? Yeah, not all words are distributed evenly. In the ideal world, a hash function would allow a pretty even distribution, so all of the lists are about equal length. But you can imagine we're going to get a really long A list and probably a pretty short Q or X list, for instance. So that would be one drawback. And you might also imagine that as we add the number of buckets, we can decrease the average length of each list. And so that might be helpful, too. And so we might want more than 26 buckets. We might want hundreds or thousands of buckets, for instance. And you can imagine finding a hash function that would fit that too. Questions about hash tables as a data structure? These combined a lot of the ideas we were talking about, arrays and pointers and linked lists, functions, all to achieve this goal. Yeah?
What's the use of unsigned?
Oh, yeah, what's the use of unsigned here? Unsigned int is just a special type that represents an int that will not be negative. Unsigned means it will be 0 or positive, so just excluding negative numbers. And the reason I might do that is that an int, as being a 4-byte number, can store values, as we talked about already, between negative 2 billion and 2 billion, approximately. But that's because we allow negative numbers. And because of that, we need like half the space of the integers to go towards the possibility of it being negative. But if we assume that the integer will only ever be positive, or non-negative, to be more specific, then we can represent numbers from 0 up to 4 billion. We can represent more possible positive numbers if we assert that the number is never going to be negative. And so just a trade-off there to give us more headroom in terms of space for positive numbers. Other questions? All right. Other data structures we talked about were trees. The idea of a tree is just that every node has pointers to its children. And so you can imagine a tree structure whereby we had a node that had children, and that node had individual children. So we talked about this in the abstract, but it came up much more concretely recently in the last couple weeks when we talked about JavaScript. And we talked about representing our HTML page, our website, as a tree, whereby our HTML body contained like a head element and a body element. The body might have contained like a table and a list or other things. And so we did have this idea of nodes with children. And JavaScript gave us features for being able to manipulate the DOM tree, which we'll talk about a little bit later. But it gave us that functionality as well. Another example of a specific type of tree we saw was a binary search tree. In other words, a tree whereby anything less than a particular node is located to the left of it, and anything greater than a particular node is located to the right of it, such that if I'm looking at this particular data structure and asking myself the question, like, where is the number 30? Is the number 30 in this tree? I might start with the number 28 and say, all right, start here. Is 30 greater than or less than 28? Well, it's bigger than 28, so go to the right. 38, all right, that's too big, so go to the left. And all right, we found 30. So data that's organized in a particular way, such that we can really efficiently look things up. And this was very akin to what David did in the very first lecture with the phone book of like dividing the phone book in half and half and half again and again and again, cutting the problem in half in order to binary search his way down to finding one particular name. So that was yet another example of what we could do. Then the last data structure we explored that week was tries. And so this was yet another way of trying to organize our data, in particular for storing something like a dictionary, whereby each node had two parts to it. It had a Boolean value for whether or not that node represents a word or not, and then an array of children nodes representing each of the possible letters of the alphabet that would come next. So if I had a word like cat, for instance, you might imagine that in my initial array, the first letter is C. So C is going to point me to another node Then I'm going to take the second letter A. That's going to take me to yet another node. And then I'd find like the letter T somewhere in this array and check whether that flag is set to like, is it a word or is it not a word? And that determines whether or not the word cat is inside of my dictionary or not. So this was an alternative approach to the spell checker rather than using a hash table. And what might have been the advantage of doing something like this? We talked about like time complexity for the efficiency of lookup. What is the time complexity, or how much time does it take to look up a word in a try? Well, if I have a word like cat, to look it up, I take the letters in the word cat, go C-A-T, and I found it. And what's interesting about the try is that it doesn't matter how many other words are inside of my dictionary. There could be 1,000 or 1,000,000 other words in the dictionary, and the time it takes to look up the word cat is going to be constant, or just dependent upon the length of the word itself, because all I need to do is follow the length of the word, and then I find out whether it's a word or not. And it doesn't matter what other words might be in the dictionary. Whereas in the case of a hash table, as we saw before, like it does matter that if there are a lot of words that start with C, it's going to take me more time to look up whether or not a word that starts with C is inside of my dictionary or not. So tries give us, at least in the theoretical sense, what we would call constant time lookup, the ability to, regardless of how big the input is, regardless of how many words are in the dictionary, always look up a word in a constant number of steps. Questions about that? Or about any of the other data structures that we've talked about so far? All right. Other questions about C, or the world of C, before we move on into the world of the internet and web programming? All right, so week 5, we sort of changed gears, moved into some new topics, started talking about the world of the internet. And in particular, we started with this talk about TCP/IP, which are two different protocols, the Transmission Control Protocol and the Internet Protocol, that decide how information on the internet is exchanged, how it is that we send requests to servers, get back responses, and how the internet fundamentally works. And so you might imagine that the whole idea of the internet is that I have a computer and someone else has a computer, and I want to send information to someone else's computer. Maybe my computer is like Google server trying to send the homepage to someone or whatnot, or me trying to request information from a website, for instance. So the first thing that I need is that every computer on the internet needs some unique way of identifying that computer. Like we need some way of knowing which computer we're asking information from, which computer we're sending information to. And so how did we solve that problem? How did we identify devices on the internet? IP addresses, great. IP for Internet Protocol, where every computer gets an address, just number.number.number.number, representing what that computer's address happens to be. And then in order to send information from one computer to another computer, we would send these messages. And what needs to be contained inside of the message, inside of the proverbial envelope that sends information from one computer to the other? Well, we need a from address. Who is information being sent from? I'm sending information from my computer. What else needs to go here? To, yeah, who am I sending information to? What IP address is going to receive this information? And what else? Yeah, a port number. So this was a little bit weird, but the internet's composed of a lot of different services, right? You can look at web pages, you can look at email. There's also something called FTP for transferring files. So a lot of different services that you can do over the internet, and the port sort of determines which service I'm specifically referring to. So there's a specific port for email and a specific port for web pages, like 80, for instance, for HTTP, that gives me some sense as to, on the receiving end, when I get this packet, what do I do with it? Should I interpret this as a web page or an email or whatnot? The port gives me that sort of information. And another thing TCP/IP does is divide information up into packets. Right? It would be expensive if the entire web page, a big web page with a lot of images and other content, were sent as one big packet through the internet. It's much easier for things to pass as smaller packets. And so each packet of information is going to be labeled with a number. This is packet 2 out of 4, such that on the receiving end, if I get a packet 2 out of 4, I better expect I should also be getting a packet 1 and a packet 3 and a packet 4 as well. And I need this information so I know how to stitch that information back together once I open up these packets and see what's inside. And so this was TCP/IP, this idea of using these protocols, these rules that we've agreed on, for determining how to transfer information over the internet. So when we actually type in something like google.com or harvard.edu or yale.edu into a web page, we're not typing in the IP address that we want to request things from. So how does that process happen? How does our computer know when I type in google.com what its address is? Well, that's using another service, DNS, the domain name service, for saying, given some URL, some host name, what IP address does it live in? And your computer might know some of these. There are also DNS servers whose sole job is to say, take an address like harvard.edu, and let me tell you what its IP address is, such that you can actually go there. And this just makes our lives a little bit easier. Rather than have to memorize all of these IP addresses and type those into our web browsers, we can type in more human-friendly host names and get back responses a little bit more cleanly. Next up, we talked about HTTP, yet another protocol, the Hypertext Transfer Protocol, for how we make and send web requests. And a request might look something like this. Get slash is something we saw at the beginning of HTTP, but is hopefully more familiar to you now that you've built a couple of web applications, where get right here is the request method. You can request a page in a number of ways. Get meaning just like get this page. Maybe you've used post before for like send data to a particular endpoint. And so get and post are two examples of request methods. Now, what route specifically am I requesting information from? This slash just means the default route, get me the home page, for instance. HTTP 1.1 is just the version of HTTP that I'm using. And then what host? What am I sending information to? In this case, harvard.edu. And so that's what an HTTP request, at least in the header section of it, might actually look like. And then when an HTTP response came back to me, it could come back with any number of status codes for deciding whether or not the request succeeded, or if it failed, what part of it failed. And so HTTP 200, what did that mean? If I make a request and the response comes back with status code 200, that means what? All good, great, everything's OK. 200 means OK. The request succeeded, and probably the page just loads. But there are other things that can happen as well. 301 we looked at for like something's been permanently moved. If one address is redirecting me to some other address, you can redirect them using a 301 response code. 403 means like forbidden. You're trying to access a page you're not authorized to access. 404 is one you've probably seen a lot, meaning not found. Like this page just wasn't there. I tried to access a page that didn't exist. And then finally, 500, one you may have seen over the course of the last 2 weeks working on these problem sets. What does 500 mean? Yeah? Internal server error, usually some problem in our server. And as we've been writing web servers in these last couple weeks with Flask, if something's not quite right, odds are you've gotten at least a couple of these 500 errors, meaning something went wrong in the server. And that generally means there's some bug in your Python code that you need to go back and try and figure out why something went wrong or why a particular case wasn't handled. And so 500 is the error code for that. And there are many other HTTP status codes more than these were the ones we focused on, but certainly they're ones you could look up online, get a sense for what they are and what they do. So these were some of the basic protocols of the internet: TCP, IP, DNS, the DNS system, and HTTP. What questions do you have about that? All right, so we were able to use that information then to be able to actually start to build web pages. So we built web pages using HTML, Hypertext Markup Language, which is a markup language that let us describe the structure of a web page. And that web page might have looked something like this, where we have these nested HTML elements, whereby we have the HTML of the entire page, inside of which there's a header, and the header contains a title. The title is just hello. The HTML body also contains like the body of the HTML page, inside of which is just hello world, for instance. And we've built more sophisticated web pages than this now. But this is the basic idea, this idea of nested HTML elements composed within each other, each one of which having potentially children elements. And you could imagine organizing this information into a tree, for instance, of all of the different tags that are, or elements that are nested within each other. In order to style the HTML, we introduced yet another language, CSS, that gave us the ability to describe the aesthetics of the page, to be able to say, for a particular HTML element, let's assign it one or more CSS properties and CSS values. Or I might say color : blue, to say color this text blue, or You could change the font size or the background color or the margin or the padding around elements just to describe how the element actually looks using CSS. And we could style not just elements, but if I had like a particular element that I wanted to style. If I had multiple headers, but I only wanted to style one of them in a certain way, how would I do that? An ID, yeah. And so if I gave an HTML element an ID, I could then say for any element with ID of this, give it these CSS properties. And inside of an HTML page, there should only be one element with any particular ID. And if I had multiple elements that I wanted to style in a particular way, then I could use CSS classes for that, where a class is very similar, but if I give a class value to an HTML element, then the idea is there can be multiple things with that class name, but anything with that class name is going to get these particular CSS properties. And so that was CSS, yet another way to describe our page, this time the aesthetics of the page. And then we introduced, in fact, a third language in that lecture, not just HTML and CSS, but JavaScript, which is actually a programming language that's designed to run on the client, on the user's web browser. Now, later on, in a moment, we'll talk about Python, which we were using on the server side to be able to run our web server. Why might we want JavaScript code? What are the use cases?
To run something locally, to run to a specific idea, like a login or something along that idea.
Yeah, so things that are happening locally on the computer. And why might we want things happening locally on the client instead of going to the server? Like, what benefits there? What are the trade-offs? What do we gain? Yeah?
After the page is loaded, it just works dynamically.
Yeah, so after the page is loaded, you can dynamically ask for more information. So this was the idea of AJAX, as someone mentioned. This idea of, if I want to get more information from the server after the page is already loaded, I can use JavaScript to do that. If you've used like Twitter, for instance, and you notice that, OK, after a certain amount of time, there are more tweets that show up, you don't have to refresh the page, but it tells you, oh, there's like 2 new tweets that you can load. Or if earlier in the week you were watching on like the New York Times website, watching the midterm election, for instance, and you didn't have to refresh the page, but as calls were being made and decisions were coming in, states were changing colors, things were dynamically updating. This was because the New York Times webpage, using JavaScript, was making additional requests to their servers, asking for more information via AJAX, such that you didn't need to refresh the page over and over again. JavaScript was taking care of the job of asking for additional information. And when it got that additional information, it was able to update the DOM. So we talked about trees just a moment ago. The DOM, or the document object model, is this idea of representing our HTML page like a tree, with a node like HTML that has children, a head element, a body element. The body has hello world. The head has a title. Inside of the title is the word hello. And so JavaScript gives us the ability to take this DOM and manipulate it, to say we want to add elements here, modify what the contents of particular elements are. And so JavaScript allowed us to do that. And jQuery, which someone asked about, was just a library that made it easier to do particular things, like make AJAX requests, made it a little bit easier to select part of a page and update it, for instance. Questions about that? 3 new languages over the course of one lecture: HTML, CSS, and JavaScript. OK. The next week, we introduced yet another new language. We spent the whole first half of the class just basically doing C. And now suddenly, over the course of 2 weeks, we've introduced 4 new languages. Week 6, we introduced Python. But the goal here was not to suggest that there was a whole lot more to learn, but just that we now have this new language that shares a lot in common with languages like C and JavaScript. The syntax is a little bit different, but in particular, what was the advantage of Python? What did it give us that would have been tougher before? Why might you prefer to write a Python program than a C program? Abstraction, exactly. This theme of abstraction, this idea of we don't need to worry anymore about dynamically asking for memory and managing our pointers ourselves and freeing up memory when we're done with it. That's all abstracted away for us. Python takes care of all of that, and it gives us a more abstract way of interacting with our data, which lets us do things a little more succinctly. It makes it a little bit easier on the programmer. And what were the trade-offs there? Like, if Python is so much easier and lets us think in these abstractions, why bother learning C? Yeah, runtime would be one example of a trade-off there. Certainly it saves time in maybe writing the program, but in running the program, because you have so much more precision and control over C, it might take longer to run a Python program than it would take to run a C program. So all right, we'll fly through some of the Python syntax. Most of this is stuff that you've probably been working with for the last 3 weeks, but we could define variables, integers, and strings, and Boolean values, for instance. If we wanted to print things, we could call a function called print instead of printf, passing in a string as usual. Print automatically adds the new line, so we didn't need to add the new line. But if you wanted, you could specify what the line is going to end with by providing an additional named argument to the function. You could print out a variable if you wanted to. You could print out multiple things if you wanted to by separating them with commas, for instance. And so all of that you could do using the print function. We looked at conditions. And what's the difference between Python and C with respect to indentation? Yeah?
If there's no indents, it won't work.
Yeah, in Python, if there's no indentation, it won't work. The indentation is part of the way that Python understands like what's inside of the if statement, what's inside of the else statement. In C, that indentation is optional. It's not strictly necessary, but it's often good practice anyways for stylistic reasons. It makes the code more organized, makes it easier to read. But in Python, since we don't have curly braces around our functions and around our if statements, everything needs to be indented to mean this is inside of the if statement. Likewise, we'd use elif instead of elsif for doing conditions. We had lists of elements such that we had lists instead of arrays. And a list in Python has some additional features that the array didn't have. The array couldn't change its size, but the list can. You can append to a list. You can, in order to grow to the size of the list, you can remove things from lists, which you weren't able to do with arrays as easily in C. So adding new features, but potentially at the cost of time and memory, for instance. Loops were a little bit simpler in Python. For I in range 5 was the way of looping from 0 up through 4, so not including 5. We could run a loop that way. We could also loop over a data structure. If I had a list of items, in C, the way I likely would have done something like that is to have like a for loop, saying for I equals 0, going through all the items, print out array, square bracket I to get each individual item. Python makes it a little bit easier. It lets you say something like, for item in items. In other words, for this variable items, which is some sequence structure, like a list, for instance, let's go through each individual item and, in this case, print it out. So different ways of organizing our loops, hopefully to make things a little bit simpler. We also had functions in Python, very similar in spirit, but what's the difference here? What do we not have here that we did have in our C functions? Anything you notice that's missing? Yeah? Our variable types, exactly. And this is something more broadly that we'll notice in Python, that these variables A and B, in C we would have needed to say like int A, int B. But here we just say A and B. So Python is what we would call dynamically typed, that it infers the type, that if you pass it the number 28, it knows, OK, 28 is an int, so treat it like an int and not like a string or something else. Whereas in C, you had to explicitly tell it. So yet another distinction between these languages as well. Python also gave us access to a whole bunch of data structures. So we saw lists, which were like a sequence of elements, sort of akin to arrays, but they give us the ability to add things to the list, remove things from the list, for instance. We also had what were called like tuples or tuples, as they're often pronounced, for representing multiple like pairs of information, for instance. Like if I had a coordinate point on a grid that was like latitude, comma, longitude, or x, comma, y on a coordinate plane, and I wanted to return both of those values, an x, comma, y value, I could return a tuple, return these two items joined together into one structure that contained both of them, for instance. We also had sets. And what's the difference between a set and a list? Yeah. Go ahead. No repeated values in a set. A set, all of the elements are unique. What's the other difference? Or the other main difference, yeah? Sets are ordered or unordered? Unordered, great. So a list is stored in order. There's a first element, second element, third. Inside of a set, there's no ordering to any of the elements. They're all in the set, and you can ask questions like, is this value in the set? I can add a value to the set. I can remove a value from the set. but I can't say, like, get me the first thing in the set, because there's no ordering to elements in the set. They're all unique, but there's no order in particular to them. And then finally, a dictionary was one that we used a lot, especially in this most recent week, to say things like, if I want to relate keys to values, how do I do that? And a dictionary was a way to do that, such that if I wanted to, for instance, represent like stocks, for instance, in this most recent example for this most recent problem set, I might have had a dictionary that had, for instance, like a symbol which would be equal to some value like NFLX for Netflix, and you might have had price, which is equal to, I don't know, $10.50. It's probably more than that. I don't actually know what Netflix's value is right now. But the idea here is that we've related keys, symbol and price, with their values, Netflix and 1050, for instance. And so dictionaries give us this ability of saying, all right, here's the data structure. Let me look up what the symbol is. Let me look up what the price is. In the same way that you look up a word's definition in a dictionary, like an English word dictionary, in a Python dictionary, we take the keys, we look up the keys in the dictionary, and we get their values. And so that was a useful data structure to be using in this most recent week, and it's a data structure that comes up a lot, not only in Python, but also in the world of JavaScript. JavaScript objects are often represented this way as well, using something called JavaScript object notation, or JSON, just an easy way of interchanging information across the internet or between two parts of a program, for instance. So questions about Python data structures, lists, sets, dictionaries, or otherwise? So good question. The question was about switch statements. Python itself doesn't have switch statements per se, but you can emulate that type of behavior using a dictionary by looking at conditioning on particular keys that are inside of the dictionary. And there are Python functions for like extracting the keys from a dictionary, for instance, which you can do as well. All right. Questions about Python before we move on to web programming? All right, 2 weeks left, and we're really nearing the end of the semester at this point. Web programming was the idea of combining all of this all together. And the first thing we talked about here was this paradigm of Model View Controller, or MVC, which is a way of organizing our web application together with a model, the view, and the controller as different components or different parts of the application. And so if we visually try to think about what MVC actually means, how are we organizing our web application? What is the model inside of our, what's actually inside of the model when we think of the model of our web application? HTML is part of the web application, good thought. It's not quite in the model. When we talk about the model, we're usually talking about the data of our web application. So our model is often going to represent the database from which we're drawing our information. So our model is like our finance.db file that represents this idea of, all right, we've got shares of stock, we have users and whatnot, other types of information, for instance. And that's on the back end. Somewhere in our server, we're storing that database. And then on the front end, what the user sees is the view, which is like our HTML and our CSS code, all the stuff the user actually sees on the page. That's the visual stuff, the view that they see. And maybe they're seeing a representation of the data inside the model. Maybe they're seeing a table of all the stocks that they own, where that information is drawn from the model. But it's not like the user is directly talking to the database. It's that your controller, some web application in this case, is talking to the model. It's getting data from the model. And it's sending that data in some representation form to the view, for instance, whereby using something like db.execute, for instance, you might be querying for information from the database in order to say, get me this data from the database. You might be processing it some way. Maybe you're looking up the values of stocks, for instance. You generate some table to display things nicely, and you display that to user in the view. And of course, these arrows don't just point in one direction. Maybe when the user submits a form, they're submitting some form to try and log in or look up a quote or try to buy a stock. They're submitting requests back to your web application, back to your controller. And if ever you need to update your database, your controller might be taking care of adding rows to the database, updating your model, so to speak. So there's this interaction here between the model, like the data of your program, the controller that's actually doing the interesting logic of handling user registration, about looking up stock quotes, for instance, and then rendering the view, which is ultimately what the user sees when they go to your page. And so that's this idea of the model view controller paradigm, of these different parts of the web application that all interact together in order to be able to function as a cohesive whole. Questions about that? And to use that, at least in Python, we used a framework called Flask. And Flask just made it a little bit easier to design a web server. Rather than have us write everything, we could just basically say, when a user goes to this route, like the / route, then go ahead and run this function, where that function is just going to render some HTML template. And of course, things got a fair bit more sophisticated than this, because maybe we wanted to handle both GET and POST requests and handle them differently. When you try to get data, maybe you're just going to say, display a page. But when you post data, sending data to a particular route, maybe you want to process that data in some particular way, updating your database or querying for values from the database, for instance, in order to perform some sort of, to get some sort of result. And so that was definitely something you could do as well. And these functions might end up being longer, doing some logic, some in Python of the processing of data, ultimately rendering some view. And if you wanted to provide information to that view, if maybe index.html wasn't going to be the same HTML page every single time, then we could take data from the controller and pass it into our view, providing arguments to this render template function to give our HTML file the ability to be a template. And we actually used a templating language called Jinja for the course of this class, whereby you could insert a value, like a variable value, into an HTML template by using that like double curly brace notation, meaning like insert some variable's value here. And we likewise did something similar, where you could have like Python logic inside of your web application, whereby in Jinja you could do something like have curly brace %, for item in items. And you could actually run some loop that was generating like some list item that contained some data here that contained the list item inside of your for loop. So you can have a for loop inside of your Jinja code, or conditions, like if statements, inside of your Jinja code that would template your HTML in a particular way, that would not just render the same HTML every single time, but dynamically generate HTML, generate new HTML depending upon what user is logged in or what stocks they own, for instance, showing them something different every single time. Or in the case of survey, showing them a table with the results of the survey where you didn't write the HTML code for each of the responses. You were just reading from a CSV file and then displaying those results inside of an HTML table. And so we had that capacity as well. Questions about Flask and how that relates? Again, it's not depicted here, but we could query from like the database in order to ask for data as well, getting stuff from the model, then expressing that by displaying things in the view, all connecting back to this model view controller paradigm. All right, yeah?
Too far. The app Flask name, now, is that just a placeholder name? Was that always named?
It always is actually going to be __name___. This is a keyword in Python that sort of refers to like the file that's currently being run. This just generates the app. And this line is usually written for you in the distribution code we've given to you, so no need to worry about it too much. All right, finally, our last week of the class was this most recent week, all talking about databases, in particular SQL or SQL, the database language that we were using in order to interact with, in our case, what we called a SQLite database. And so a database, you can think of as just a whole bunch of tables, where each table, again, has rows and columns of data. And each of these pieces of data had a type. This idea of types is coming back. We didn't have to be specific about types in Python, but we do have to be specific about types in SQL, where we might say we have an integer type, or maybe if we don't need that much space, a small int or a big int. We had numeric types for other numeric types of data, real number types of data. Then for representing text, like characters, we had char n and varchar n. Anyone remember the difference between these two?
Char is a defined length every single time. Varchar is variable character length.
Yeah, exactly. Varchar is variable character length. So char of 10, like char 10, means I am storing data in this column that will be sequences of 10 characters. And here varchar n is, all right, this could be up to 10 characters, but it could be less. It could be anywhere up to that amount. And so as we were designing our databases, database design is a big piece of like the design of our web application. What are the columns of our database table? And what are the types of each of those columns? What makes the most sense? And there are some decisions to be made here that if you could go like varchar 5,000 for everything, but that might be more space than you actually need. If you don't need that much space, no reason to ask for that much, for instance. So in order to create a table, we use syntax that looks something like this, creating a table in the lecture example of a table of registrants. Yeah, question? Timestamp and time. Good question. Let me get back to you on that. In short, they're likely just a formatting thing of the different ways that that information is stored, but I'll check on that for you. All right, we're creating a table called registrants. In this case, it's storing 3 columns, ID, name, and dorm. ID is an integer, and it's the primary key. What does primary key mean? Yeah, it's like the main unique way via which I'm going to identify registrants, that maybe 2 registrants have the same dorm, or maybe 2 registrants have the same name, but I know that the ID I can use to uniquely identify every single row inside of this table. So oftentimes you'll find tables that have an ID column in the same way that Excel or Google Sheets gives you like a number next to every single row. This is the same idea, that every row gets a number such that if I want to refer to row number 28, it's always going to be that row. Every table also has a name column for someone's name up to 255 characters, and a dorm of up to 255 characters, though realistically it might be less. And then we had queries. We could insert things into databases by saying, insert into this table these 3 columns. What values go in those 3 columns? 1, David and Matthews. You specify what values are going in those columns. You could select things from a table. If I want to get data out of a table, select star from registrants means get me everything from the registrants table. And yeah, question?
What's the difference between having a primary key and a unique index? Yeah, like that was something I was mentioning last week.
Yeah, good question. So the question is a little bit about primary keys. This becomes particularly important because oftentimes you will want to have other tables that reference the primary key of a different table. So for instance, in the case of our registrants in the example that I just showed, you might imagine a case where you would have like a table called dorms, whereby that dorms table would have an ID column and it would have a name column for all of the dorms that people could live in. And maybe ID 1 is Canada, and ID 2 is Pennypacker, and so on and so forth. I should have picked a shorter name. And then in the registrants table, an entirely different table, you might have columns. You might have an ID column, and you might have a name column for the name of the registrant. But rather than storing a dorm, you could instead, like a common paradigm is to reference the primary key of some other table. In this case, something like dorm ID. This is what we would call a foreign key, saying this is going to reference the primary key of the dorms table, such that rather than store, like, if ID 1 is Brian and I lived in Pennypacker, rather than writing Pennypacker as the dorm ID, I could just say 2, meaning reference the thing that has ID 2 inside of the dorms table, and then using what we call a SQL join, I could actually join these tables together and actually get the information that I wanted. But this is often a cleaner way of representing that data, such that if I have a lot of people from Pennypacker, rather than store the whole string Pennypacker again and again and again, I could just include it once. And you might imagine this is useful if I ever need to update, like if Pennypacker ever changed the name of what the dorm's name is, well, I change it here, and it's going to be correct for all of the registrants, rather than having to change it everywhere across a larger space of data. So we can get data from a table. Select star from registrants. If I don't need all of the columns, you can specify just which columns I want to extract by doing something like select name, comma, dorm from registrants, meaning just get these 2 columns. And this query will get you all of the registrants, but maybe you only want certain of the registrants. You might want select name, comma, dorm from registrants where dorm equals Matthews, for instance. And so you can select just particular registrants by doing a query, by limiting the amount of data that you're actually getting back. You can update the table. I'm just going through the syntax relatively quickly because hopefully it's stuff you've seen before. Updating registrant, setting name to David Malin where ID is 1 if I want to update the value in a table. And likewise, if I want to delete a registrant whose ID is 1, there's SQL syntax for that as well. So we have these basic operations: creating a table, inserting rows into a table, selecting data from a table, updating a table, or updating entries in the table, and then deleting entries from a table, all using these basic commands. And we can link those together with Python to be able to say that using like db.execute, I would like to execute this statement inside of a web application, such that when a particular request is made, I can request for a particular operation to happen as a result. So we talked about this already, this idea of foreign keys and joining tables, which often works well when you've got multiple tables, like a dorms table and a registrants table. I can link the 2 of them together. And so what are things that could go wrong? We talked about race conditions first. Anyone remember what a race condition is? So a race condition happens, or can happen, when 2 entities are trying to access the same piece of data at the same time. Like you imagine that if I went to a bank, for instance, and inside of my bank balance, I have $100. And I have 2 people with the same ATM card, the same debit card or whatever, go to an ATM and try and withdraw $100 at the exact same time. Well, what's going to happen there? Well, one person might ask to withdraw $100, and they might ask the database, like, do you actually have $100 for me to withdraw? And the database might respond, yes, you do have $100 that you can withdraw. And the other person is asking the database the same question, do you have $100 that I can withdraw? And the database responds, yes, because there is $100 here. And all right, the database said yes, so the database goes ahead and gives this person $100, gives this person $100, and the result is that you might end up with a situation where now, even though I only had $100 in the bank account, somehow I've gotten $200 out of this exchange by taking advantage of this race condition where 2 people trying to do the same thing at the same time, or even different things at the same time, could run into problems with our data. And so how did we solve this? Anyone remember? What do we do about it? Yeah?
Banks may put a hold, like as soon as one thing happens, they may put a lock on it so no one else can try to get in.
Yeah, something like a lock would be a way to solve this. Like when one person starts an operation, lock the database until that person is done, then unlock it, and then the next person can take advantage of it. Those locks are something that you see a lot in computer science as a way of trying to solve problems of synchronization, of multiple people trying to access data at the same time. And then the other threat or vulnerability we saw were SQL injection attacks. This is what could happen if you're not careful about how you deal with your inputs. If you allow a user to just type an input and you put that input straight into a SQL query, you could run into an issue where you're allowing the user to run any SQL command they want on your database, and they could insert arbitrary rows in the database, delete the database if they wanted to. So that's another security threat just to be mindful of. And what are potential solutions for that? How do we deal with SQL injection? So what we had you do in this problem set, at least, was to provide any input as like parameters to your db.execute query. And what that would do is escape those characters. In other words, anything that could be like a dangerous character, like a semicolon, for instance, it would appropriately handle that, or a quotation mark. It would appropriately escape those characters such that you wouldn't end up with a situation where arbitrary SQL is actually getting executed, and you're only executing SQL queries that you actually intend to run. And so that was the idea of SQL. Any final questions about anything across the entire semester? We covered 9 weeks of content in a little under 3 hours, so a lot of material. Yeah?
Will this presentation be on CS50 website?
Yeah, it's actually being live streamed now. It'll be available to watch afterwards via video as well, and I can post the slides from it online too. All right, there are more office hours later today in terms for design for quiz preparation in order to ask questions for that as well. With that in mind, the quiz is going to be released tomorrow at noon, so just be aware of that. You'll have until Thursday in order to work on it. Best of luck, and feel free to email in the meantime with any questions. I'll stick around for a little bit to answer questions too.